The data dropped at 7:47 Eastern Time on October 29, 2025. David Farnokia, a navigation engineer at NASA's Jet Propulsion Laboratory, filed a report that would send shockwaves through every observatory on Earth. 3I-ATLAS, the interstellar visitor we've been tracking for months, isn't following gravity anymore. It's accelerating, radially away from the Sun at 135 km per day squared, transversely at 60 km per day squared. Small numbers, yes, but real, measured, confirmed. And if this object is a comet, if it's natural, then in the next 30 days it must lose 10% of its total mass. 10%. That's 5.5 billion tons of material erupting into space, creating a plume so massive that every telescope from here to Jupiter should see it blazing across the solar system. But here's what keeps me awake at 3 in the morning. What if we don't see anything at all? If you're new here, hit that like button and subscribe, both help this channel grow more than you know. Tell me in the comments where you're listening from, what time it is there, and whether you think we're looking at the biggest cover-up in astronomy or the most misunderstood comet in history. The 4 arc-second deviation. October 29th was supposed to be predictable, perihelion, the closest approach to the Sun. Every comet, every asteroid, every chunk of rock and ice that's ever passed through our solar system follows a path dictated by gravity. Newton's laws, Einstein's corrections. The mathematics are elegant, precise, tested across centuries. You plug in the mass, the velocity, the position, and you know exactly where that object will be in an hour, a day, a month. The universe doesn't surprise us with trajectories. It can't. Gravity is deterministic. Except 3I-ATLAS showed up 4 arc-seconds away from where it was supposed to be. 4 arc-seconds doesn't sound like much. It's a fraction of a degree. If you held a dime at arm's length, 4 arc-seconds would be roughly the width of a human hair seen from across a football field. Astronomers work with these tiny angles all the time. They're accustomed to precision at scales that make the rest of us dizzy. But here's what matters. 4 arc-seconds at a distance of 203 million kilometers from the Sun translates into a real spatial deviation, a measurable offset from the gravitationally predicted trajectory. And the only way to get that offset is through a non-gravitational force. The ALMA telescope, the Atacama Large Millimeter Array, caught it first. ALMA sits high in the Chilean desert, an array of 66 radio dishes working in concert, peering into the cosmos at wavelengths invisible to human eyes. On October 29th, as 3I-ATLAS reached perihelion, ALMA's operators noticed something strange in the positional data. The object wasn't where the JPL ephemerids said it should be. Not in right ascension. The discrepancy was small but consistent across multiple observations, enough that David Farnokia, who specialises in orbital mechanics and near-Earth object trajectories, flagged it immediately. Farnokia has spent his career calculating the paths of asteroids and comets. He earned his PhD in mathematics from the University of Pisa, spent years refining the models that predict close approaches, potential impacts, orbital evolution. When he filed his report to the JPL Small Body Database, he wasn't speculating. He was documenting a measured phenomenon. 2 acceleration components, radial, pointing directly away from the Sun, transverse, perpendicular to the Sun's direction. Both real, both requiring an explanation. For a comet, the explanation is supposed to be straightforward. As the nucleus heats up, volatile ices sublimate, turning directly from solid to gas. Water, carbon dioxide, carbon monoxide. These gases jet outward from the surface carrying dust and debris. The momentum of that ejected material pushes back against the nucleus itself, like a rocket engine burning in reverse. It's called the rocket effect, and it's been observed in hundreds of solar system comets. Perfectly natural, perfectly understood. But here's where the numbers start to scream. Momentum conservation is not negotiable. If 3I-ATLAS is accelerating because of outgassing, then the mass it ejects multiplied by the velocity of that gas must equal the mass of the nucleus multiplied by its change in velocity. You can rearrange that equation to calculate how fast the comet is losing mass. Avi Loeb did exactly that, and the result is brutal. If the acceleration Farnokia measured comes from sublimation, then 3I-ATLAS is evaporating with a half-life of about 6 months. 6 months. That means over the roughly 1 month it took to cross the perihelion distance scale, it would have lost at least 1/6 of its total mass. 1/6. The Webb telescope measured 3I-ATLAS's mass loss rate back in the spring. 150 kilograms per second, steady, continuous. For 5 months, that rate didn't produce any detectable non-gravitational acceleration. From that, Loeb and his team calculated that the nucleus must weigh at least 33 billion tons. It's a massive object, bigger than anything we've seen from interstellar space, bigger than Oumuamua by a factor of 1,000,000, bigger than Borisov by a factor of 1,000. 33 billion tons is a lot of ice and rock, but 1/6 of that is 5.5 billion tons. 5.5 billion tons of gas and dust that should be erupting into the space around 3I-ATLAS right now, forming a coma so vast and bright that it would be impossible to miss. Think about what 5.5 billion tons looks like in space. Imagine every building in New York City, every car, every bridge, every subway tunnel, all of it ground into powder and launched into the void at hundreds of meters per second. That's the scale we're talking about. A plume of material that would dwarf the nucleus itself, glowing under the sun's light, scattering photons, emitting spectral lines from ionized gas. The kind of display that amateur astronomers could photograph from their backyards. The ESA's JUICE spacecraft, currently en route to Jupiter, will pass within 64 million kilometers of 3I-ATLAS on November 4th. JUICE isn't designed to study comets. It's built to explore the icy moons of Jupiter, to search for subsurface oceans, to map magnetic fields and radiation belts. But it carries cameras, it carries spectrometers. If there's a massive cloud of gas around 3I-ATLAS, JUICE will see it. No question. The geometry is perfect. The distance is close enough. The instruments are sensitive enough. And if JUICE sees nothing? If the images come back showing a faint compact nucleus, with no significant coma, no expanding shell of debris, no sign of the catastrophic mass loss that the non-gravitational acceleration demands, then we have a problem. A big one, because the numbers don't lie. Either 3I-ATLAS is hemorrhaging material at a rate that should be blindingly obvious, or the acceleration isn't coming from sublimation at all. Loeb laid it out in his blog post on October 30th. He walked through the math step by step, showing his work, citing the Webb data, referencing the JPL orbital fit. He didn't hide behind jargon or hedge his conclusions with maybes. He said it plainly. If we don't observe a massive gas cloud in November and December, then the non-gravitational acceleration can't be explained by cometary evaporation. And if it's not evaporation, then what's left? This is where the conversation gets uncomfortable for a lot of astronomers. Loeb has been here before, with Oumuamua. That first interstellar visitor showed a non-gravitational acceleration too, but Spitzer, the infrared space telescope, looked for the gas and dust that should have accompanied it. Found nothing, not a trace. Oumuamua accelerated without leaving any visible trail. The comet experts invented a new term to explain it: dark comet. A comet that doesn't produce a visible coma or tail, but still outgasses enough to push itself around. Loeb has pointed out with characteristic bluntness that calling something a dark comet is like calling a cave dweller's cell phone a shiny rock. It's a label that avoids the harder question. If an object accelerates without producing the gas that supposedly causes the acceleration, maybe it's not a comet at all. 3I-ATLAS was supposed to be different. It has a coma. It has a tail. Hubble imaged it back in July, showing a teardrop-shaped cocoon of dust streaming away from the nucleus. Ground-based telescopes detected spectral lines from cyanide, from nickel, from hydroxyl radicals. It looked like a comet. It smelled like a comet. Everyone breathed a sigh of relief. See? Interstellar objects. Can be normal after all. Oumuamua was the fluke, the anomaly. 3I-ATLAS would prove that interstellar comets behave just like solar system comets, just with different chemistry because they formed around different stars. But now we have the 4 arc-second deviation. We have the measured acceleration. We have the mass loss calculation screaming at us that something is very wrong. And we're about to find out if the universe is playing by the rules we think we understand, or if it's been trying to tell us something all along that we've been too stubborn to hear. November and December will answer the question. JUICE on November 4th, ground-based telescopes as 3I-ATLAS emerges from behind the Sun in mid-November. Hubble, Webb. The entire IAEWN campaign, the International Asteroid Warning Network, mobilizing observatories around the world to track this object with unprecedented coordination. They're treating it like a planetary defense exercise. which is a polite way of saying they want to know exactly what this thing is and what it's doing. On December 19th, 3I-ATLAS makes its closest approach to Earth. 269 million kilometres. Still far, still safe, but close enough for every major telescope to get a clear look. If there's a plume, we'll see it. If there's a coma expanding at the rate the mass loss demands, we'll measure it. If the spectral lines show the chemical fingerprints of massive sublimation, we'll catalogue them. And if there's nothing, if 3I-ATLAS just keeps drifting through space, compact and quiet, accelerating without any visible explanation, then Avi Loeb's question becomes impossible to ignore. What if the non-gravitational acceleration isn't a side effect of heating and sublimation? What if it's deliberate? What if something inside that object is firing an engine, making course corrections using the sun's gravity for a carefully calculated Oberth maneuver? 4 arc seconds. That's all it took. 4 arc seconds to turn October 29th from a routine perihelion passage into the most scrutinised moment in the history of interstellar object studies. 4 arc seconds to make every astronomer on the planet stop and ask the question they've been avoiding since July. What if 3I-ATLAS isn't what we think it is? Farnokia's report is public. You can look it up yourself. JPL Small Body Database. 3I-ATLAS. Scroll down to the non-gravitational parameters. They're right there. Radial acceleration, transverse acceleration, numbers with uncertainties, measurements with error bars, the kind of data that gets published in peer-reviewed journals, that gets checked and rechecked by independent teams, that becomes part of the permanent scientific record. This isn't speculation. It's not tabloid sensationalism. It's navigation data from one of the most respected orbital mechanics experts at NASA. And it says, in the cold language of mathematics, that 3I-ATLAS is not following a purely gravitational path. The question isn't whether the acceleration is real. The question is what's causing it. And in the next few weeks we're going to get an answer. Either we'll see the plume, and 3I-ATLAS will go down in history as an unusually volatile interstellar comet with extreme sublimation rates and fascinating chemistry, or we won't see the plume, and then every assumption we've made about this object, every comfortable explanation, every reassuring press release collapses. Because if a 5.6 kilometre wide object can accelerate through space without ejecting billions of tons of gas, then it's doing something we don't have a natural explanation for. Something that requires energy, control, precision. Something that looks a lot less like geology and a lot more like engineering. The clock is ticking. JUICE launches its observations in 6 days. Ground-based telescopes will have their shot in 2 weeks. Hubble and Webb are already scheduled for December. The data is coming, and when it arrives, one way or another, we're going to know. But here's the thing that keeps me up at night. The detail that makes my hands cold when I think about it too long. The timing. 3I-ATLAS reached perihelion on October 29th. That's the optimal moment for a spacecraft to burn its engine. The Oberth effect. When you're deep in a gravity well, moving at your fastest orbital velocity, any thrust you apply gets multiplied by the energy you're already carrying. It's Astronautics 101. If you want to change your trajectory, if you want to speed up or slow down or alter your path, you do it at perihelion. You do it when you're closest to the sun. And 3I-ATLAS did exactly that. Right on schedule, right when the math says it should. Was it coincidence? Did the ice just happen to sublimate hard enough at exactly the right moment to produce a measurable acceleration during the one window where such an acceleration would be most efficient? Or did something inside that object know exactly when to fire? The 4 arc-second deviation isn't just a measurement. It's a question mark, burned into the trajectory of an object that's already defied every expectation we had. And the answer, whatever it turns out to be, is rushing toward us at 61 kilometers per second. November 4th. 6 days. JUICE will tell us what's really out there. And after that, there's no going back. No more speculation, no more debate, just data. And whatever that data reveals about the nature of the third interstellar visitor to ever cross our threshold. Bluer than the sun. The coronagraphs caught something impossible on October 30th. Multiple spacecraft positioned at different points around the solar system all recorded the same anomaly. 3I-ATLAS, during its passage through perihelion, shifted its colour spectrum to wavelengths bluer than the sun itself. Not slightly bluer, not marginally different. Distinctly, measurably, impossibly. Blue. This shouldn't happen. Ever. Not with any natural comet humanity has ever observed. Qicheng Zhang and Carl Battams published their findings within hours of processing the data. Their paper, submitted to the astrophysical journal Letters, contains photometry from 4 separate instruments. Stereo Secchi cameras, both the HI-1 heliospheric imager and the COR2 coronagraph. Soho's LASCO C3, the workhorse of solar observation for nearly 30 years, and GOES 19's CCOR1, the newest addition to space-based coronagraph arrays, launched just last year for operational space weather monitoring. 4 independent instruments, 4 different vantage points, 4 sets of data showing the exact same thing. 3I-ATLAS brightened rapidly as it approached perihelion, and its light shifted blue. The colour measurements are precise. LASCO has multiple filters: blue, orange, deep red, and infrared, in addition to its standard clear filter. When they stacked all the blue filter images of 3I-ATLAS, the comet appeared 0.7 magnitudes brighter than it did in the clear filter. 0.7 magnitudes. That's nearly twice as bright. In the orange filter, still 0.4 magnitudes above clear, the comet was pumping out more light at shorter wavelengths, the opposite of what dust does to sunlight. CCOR1 confirmed it independently. Its bandpass runs from 470 to 740 nanometers, shifted about 40 nanometers bluer than LASCO's clear filter. That slight difference in wavelength sensitivity gave CCOR1 an edge in detecting the blue emission. The comet registered 0.4 magnitudes brighter in CCOR1 than in LASCO clear. Different spacecraft, different orbit, same result. Here's why this matters. Dust scatters light. Always has, always will. When sunlight hits a particle of dust, the shorter blue wavelengths scatter more efficiently than the longer red wavelengths. It's called Rayleigh scattering, the same physics that makes Earth's sky blue and sunsets red. Dust makes things look redder, not bluer. Every comet ever observed, from the great comets visible to the naked eye down to the faintest telescopic fuzzballs, has shown this reddening effect. The dust coma reflects sunlight, but it shifts that light toward longer wavelengths. 3I-ATLAS did the opposite. It outblued the sun. The only way to produce that kind of spectral shift is through emission, not reflection. Hot gas emits light at specific wavelengths corresponding to the energy transitions of its atoms and molecules. Ionization pumps atoms into excited states, and when they drop back down, they release photons. Cn emits in the violet. C2, the famous swan bands, glow green. NH2 adds its own contribution in the blue and near ultraviolet. But there's a problem with invoking gas emission to explain the blue colour. The instruments that detected this weren't optimised for gas. Stereo's HI-1 and COS2 have bandpasses that largely miss the C2 swan bands. HI-1 runs from about 595 to 720 nanometers, with some leakage into the blue and infrared. COR2 covers 670 to 750. Both are shifted too far red to efficiently capture C2 emission, yet both showed the comet brightening faster than expected. LASCO's blue filter does capture C2 efficiently, so does CCOR1's broader bandpass. The fact that these instruments saw the comet brighter in blue makes sense if gas emission is present. But HI-1 and COR2 shouldn't have been so sensitive to it, unless the gas emission was so intense that even the red tail of the spectral lines was bright enough to dominate over dust scattering, or unless something else was producing the blue light. Zhang and Battams analysed the brightness evolution carefully. They corrected for distance to Earth, accounted for phase angle, and fitted the heliocentric dependence. The result is shocking. 3I-ATLAS brightened with distance from the Sun to the power of negative 7.5 plus or minus 1. In plain language, as the comet got closer to the Sun, its brightness increased at a rate described by 1 over distance to the power of 7.5. Most Oort cloud comets, the long-period visitors from the distant edge of our solar system, brighten with a power law between 2 and 4. An exponent of 2 would mean the brightness scales purely with the amount of sunlight hitting the surface. No activity, just reflection. An exponent of 3 or 4 indicates moderate sublimation, gas production increasing as temperature rises. But 7.5? That's not moderate. That's explosive. That's runaway sublimation, or something that mimics it so perfectly we can't tell the difference. The paper's conclusion is carefully worded. the reason for 3I-ATLAS's rapid brightening remains unclear. The authors acknowledge that the rate far exceeds what's typical for Oort cloud comets at similar distances. They note the blue colour, the gas emission, the unusual spectral properties. They suggest that perhaps CO2 sublimation suppressed water ice sublimation at larger distances, and now, close to perihelion, the water ice is finally dominating and erupting violently. But they don't commit. They don't say this is definitely what's happening, because the data doesn't quite fit. The brightness curve is too steep. The blue shift is too pronounced. The whole thing feels like it's operating at an intensity level that shouldn't be possible for an object this size at this distance. Let's talk about what the blue colour really means. The surface of 3I-ATLAS, based on early spectroscopy, is red. Tholins, complex organic molecules formed by radiation processing of simple ices, coat the nucleus. Tholins are dark, reddish-brown, the colour of ancient ice exposed to cosmic rays for billions of years. They absorb blue light efficiently. They should make the comet look even redder than plain ice would. The fact that we're seeing blue, light means that light is being produced inside the coma, not just reflected from the surface. Gas molecules, fluorescing under solar ultraviolet radiation, emit at their characteristic wavelengths. This is normal. Every active comet has a gas coma, but the intensity matters. The ratio between gas emission and dust scattering determines the overall colour. For 3I-ATLAS to appear bluer than the Sun, the gas emission has to be overwhelmingly dominant. It has to drown out the dust contribution entirely. Jacques Crozier and his team at the Paris Observatory detected OH emission from 3I-ATLAS using radio telescopes. OH, hydroxyl radical, is a breakdown product of water. When water molecules leave the nucleus and get hit by solar UV, they split apart into hydrogen and OH. The OH then fluoresces at radio wavelengths. Crozier measured the OH production rate between October 13th and 19th, just before perihelion. 5.7 times 10 to the 28th molecules per second, plus or minus about 10%. Compare that to the last optical OH measurement before 3I-ATLAS went behind the Sun. September 12th. 2.19 astronomical units from the Sun. Production rate of 10 to the power of 27.15 molecules per second. Now it's 10 to the 28.76, roughly 40 times higher. In 1 month, the OH production rate increased by a factor of 40. The power law connecting those two measurements has an exponent of 8.3, even steeper than the optical brightness increase. Water production, if that's what OH represents, is ramping up faster than the dust, which would explain the blue shift, which would explain why LASCO Blue and CCOR-1 saw the comet so much brighter than expected. But it also brings us back to the mass loss problem. If water is sublimating at the rate implied by the OH measurements, then 3I-ATLAS is losing billions of tons of material. The plume should be enormous. The coma should be expanding, glowing, filling the field of view with scattered light and fluorescent emission. CCOR-1 did resolve the comet as an extended source. The stacked images show a fuzzy blob about 4 arc-minutes in diameter, compared to a nearby star that looks like a point. 4 arc-minutes at a distance of 235 million kilometres translates to about 270,000 kilometres in physical size. The coma is big, real, extended. But is it big enough? Is it bright enough? Is it consistent with losing 1/6 of the nucleus mass over the course of a month? We won't know until JUICE gets there. We won't know until ground-based telescopes can observe 3I-ATLAS against a dark sky instead of right next to the Sun. We won't know until Hubble and Webb point their mirrors at this thing and take deep exposures with every spectrograph they have. What we do know is that something about 3I-ATLAS's interaction with solar radiation is extreme. The brightness increase is extreme. The spectral shift is extreme. The timing hitting maximum activity right at perihelion is textbook behaviour for a spacecraft optimising an Oberth manoeuvre and utterly unremarkable for a comet. Comets are messy. They don't turn on and off like light switches. They don't ramp up their activity in perfect synchronization with orbital mechanics. Yet here we are. There's another detail in Zhang and Battam's paper that deserves attention. They note that the phase angle during most of these observations was very low, between 1.7 and 10.4 degrees. Phase angle is the angle between the Sun, the comet, and the observer. Low phase angle means we're looking at the comet with the Sun almost directly behind us, like seeing a full moon instead of a crescent. At low phase angles, tails can point in almost any direction relative to our line of sight, especially ion tails which follow the solar wind rather than the purely anti-solar direction of dust tails. The CCOR-1 images don't show a clear tail, just the extended coma, but the stacking process covered 6 days, during which the sunward direction rotated by 125 degrees as seen from GOES 19. Any structure aligned with the sun would smear out. Any ion tail following the wind would blur into the general coma. They note this explicitly. The absence of a visible tail doesn't mean there's no tail. It just means the geometry and the stacking process made it impossible to see. Still, there's something unsettling about an object this active showing such a compact structure. Comets usually grow long tails as they approach the sun. The most spectacular comets in history, Hale-Bopp, Yakutag, McNaught, all develop tails stretching across tens of degrees of sky. 3I-ATLAS is at perihelion, the moment of maximum activity, and we're seeing a coma but no dramatic tail structure. Maybe it's the geometry, maybe it's the dust-to-gas ratio, maybe 3I-ATLAS is unusually depleted in dust, producing mostly gas, and gas tails are harder to see from certain angles. Maybe, but maybe it's starting to pile up. Maybe this, maybe that, maybe the other thing. At what point do we stop saying maybe and start asking if our baseline assumptions are wrong? The blue colour is a fact. The brightness curve is a fact. The timing is a fact. The extended coma is a fact. Together, they paint a picture of an object undergoing intense activity at perihelion, exactly when and where we'd expect a comet to be most active. It all fits. It all makes sense. Except for the part where it has to lose 5 billion tons of mass in the next few weeks, and we're about to find out if that's happening or not. Zhang and Battams end their paper with a deliberately open statement. They write that the outlook for 3I-ATLAS's post-perihelion behaviour remains uncertain. A plateau in brightness appears as plausible as rapid fading. They call for continued observations, to provide a more definitive explanation for the comet's behaviour. Translation: we have no idea what's going to happen next. The data is weird, the physics is unclear, and we need more telescopes pointed at this thing immediately. November will tell the story. The blue light will either fade as 3I-ATLAS moves away from the sun and its sublimation rate drops, or it won't. The coma will either expand into a massive obvious plume of gas and dust, or it won't. The brightness will either follow a predictable decline curve, or it won't. And if it doesn't, if 3I-ATLAS emerges from behind the sun still compact, still bright, still accelerating without visible mass loss, then the blue light stops being a curious spectroscopic detail and starts being evidence of something else. Something that produces light without sublimation. Something that glows blue because it's hot, or ionized, or energized by processes we don't see in natural comets. The coronagraphs did their job. They captured the moment. Now, we wait to see what that moment means. The scientific civil war. On October 29th, while 3I-ATLAS was passing through perihelion hidden behind the sun, a different kind of explosion happened on social media. Brian Cox, the physicist and science communicator with millions of followers, decided he'd had enough of Avi Loeb's speculation. He fired off a post that would ignite the most public, most bitter dispute in modern astronomy. Just to be clear, Cox wrote, given recent drivel online, Comet 3I-ATLAS is a comet, made of carbon dioxide and water ices and bits of other stuff. It is entirely natural in origin, its orbit is as expected, and it will whiz around the sun and then disappear off into the galaxy again. Drivel. That was the word he chose, not speculation, not hypothesis. Drivel. He followed it up the next day with another shot. I keep seeing AI-generated content of me popping up on YouTube. The general rule is that if I appear to say something that you agree with, and you are a UFO person, flat Earth person, or think Comet Atlas 3. I is a spaceship, it's fake. UFO person, flat earther, spaceship believer. 3 categories, same tier of credibility, according to Brian Cox. If you think 3I-ATLAS might be anything other than a natural comet, you've been lumped in with people who think the Earth is a disk and vaccines contain microchips. Avi Loeb responded the same day. He didn't post on social media. He doesn't operate that way. Instead, he published a blog entry on Medium, the way he's published dozens of entries since July, calmly laying out data and asking uncomfortable questions while the rest of the astronomical community tries to pretend he doesn't exist. A few reporters asked me today about the strong statements made by the science popularizer Brian Cox, Loeb wrote, who argued forcefully that 3I-ATLAS is definitely a natural comet. I explained that Brian Cox did not write a single scientific paper about 3I-ATLAS. He acts as a science popularizer rather than a researcher who's engaged with the related science concerning 3I-ATLAS. In comparison, I wrote 11 scientific papers in recent months about 3I-ATLAS, 11 papers versus 0. That's not a rhetorical flourish, that's a citation count. Loeb listed them, linked to them, provided the Astrophysics data system identifiers so anyone could verify. 11 peer-reviewed publications, some solo, some with collaborators, all focused on 3I-ATLAS. Orbital dynamics, spectroscopy, mass estimates, kinematic origins, the WOW signal correlation, non-gravitational acceleration, every paper backed by data, every claim tied to measurements. Brian Cox's publication record on 3I-ATLAS? Empty. Not a single paper, not a single conference abstract, not a single technical note filed with the Minor Planet Center or the International Astronomical Union. Loeb didn't stop there. Rather than engage in sweeping statements, Brian should be challenged to explain the 9 anomalies associated with 3I-ATLAS. Scientific truth is not decided by a popularity contest, but by attention to data, especially when it is anomalous. 9 anomalies, not 1, not 2. 9 separate observations that don't fit the natural comet hypothesis as easily as Cox's dismissive tweets suggest. And Loeb has documented all of them, calculated the statistical likelihood of each, published the methods and results in the scientific literature. Cox has a PhD in particle physics. He worked at CERN on the ATLAS experiment, studying proton-proton collisions at energies high enough to create exotic particles. He's a professor at the University of Manchester. He's hosted television programmes for the BBC, written best-selling books, toured as a public speaker. He's brilliant, charismatic, beloved by millions of people who see him as the friendly face of science, the Carl Sagan of the 21st century. He's also not a comet expert. He's not an orbital dynamicist. He's not an observational astronomer who spends nights at telescopes collecting spectra and photometry. His expertise is in high-energy physics, in the behaviour of subatomic particles under extreme conditions. Valuable knowledge, important work, but not directly relevant to the question of whether an interstellar object is following a natural trajectory or displaying signs of technological origin. Loeb is also not a comet expert, in the traditional sense. He's a theoretical astrophysicist, former chair of Harvard's astronomy department, director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. He's published over 1,000 papers on topics ranging from black holes to the first stars to the habitability of exoplanets. He knows how to analyze data, he knows how to calculate orbital mechanics, he knows how to assess the statistical significance of anomalies, and he's led the Galileo project since 2020. A multi-million-dollar initiative explicitly designed to search for evidence of extraterrestrial technology using rigorous scientific methods. It's not a fringe operation. It's funded by private donors, staffed by credentialed scientists, equipped with custom-built observatories at Harvard, Colorado, and California. They're not hunting UFOs with shaky phone cameras. They're collecting calibrated, multi-wavelength data on aerial phenomena and space objects that exhibit unusual characteristics. 3I-ATLAS falls directly into that category. Unusual characteristics, anomalous properties, data that doesn't quite fit. And when Loeb points this out, when he publishes papers calculating the probability that 3I-ATLAS's trajectory alignment with the ecliptic plane is coincidental, or that its sunward jet is an optical illusion, or that its nickel-to-iron ratio makes sense for a natural comet, he's not making things up. He's doing the math, showing the work, inviting critique from other scientists who can check his calculations and either confirm them or find the errors. Brian Cox didn't check the calculations. He didn't engage with the data. He called it drivel and moved on. And his millions of followers nodded along, reassured that the scary alien hypothesis was just internet nonsense from attention-seeking contrarians. But here's where it gets more complicated. Chris Lintott entered the conversation too. Lintott is an astronomer at Oxford, well respected in his field, best known for co-founding Galaxy Zoo and other citizen science projects that let the public participate in real astronomical research. He's the editor of research notes of the American Astronomical Society, a journal that publishes short-format updates and preliminary findings. Back in July, Loeb submitted a paper to that journal. A straightforward analysis of 3I-ATLAS's trajectory, its alignment with the ecliptic plane, the statistical likelihood of such an alignment occurring by chance. The paper included a brief mention that if the object were of technological origin, the alignment might be deliberate, a navigation choice made to facilitate encounters with planets. Lintott, in his role as editor, contacted Loeb. He asked Loeb to remove any reference to the possibility of technological origin. Just delete that section. Talk about the statistics, fine. Talk about the trajectory, fine. But don't mention aliens. Don't mention spacecraft. Don't mention the hypothesis that the object might be artificial. Loeb refused, not because he was committed to the alien hypothesis, but because he was committed to scientific openness. The paper wasn't claiming 3I-ATLAS was definitely artificial. It was stating that if such an object existed, this is what its trajectory might look like. It was a conditional statement, a theoretical exploration, the kind of thing scientists are supposed to do when confronted with data that doesn't fit standard models. Lintott didn't budge. Remove the section or the paper won't be published. Loeb removed it. The paper came out, and then Loeb published a different paper, with different co-authors titled, "Is the Interstellar Object 3I-ATLAS Alien Technology?" He made it explicit, put the hypothesis right in the title, submitted it to a different journal where the editors wouldn't censor the question. That paper includes a disclaimer. We strongly emphasise that this is largely a pedagogical exercise, with interesting discoveries and strange serendipities, worthy of a record in the scientific literature. By far the most likely outcome will be that 3I-ATLAS is a completely natural interstellar object, probably a comet, and the authors await the astronomical data to support this likely origin. Likely natural, probably a comet, awaiting data. But still worth asking the question, still worth calculating what the technological hypothesis would predict, so that when the data comes in we can compare predictions to observations and see which model fits better. This is how science is supposed to work. You propose hypotheses, you derive predictions, you collect data, you compare. The hypothesis that survives comparison, that makes the most accurate predictions, that requires the fewest ad hoc adjustments to fit the observations, that's the one you tentatively accept until better data or better theories come along. But that's not how it's working with 3I-ATLAS. Instead, we have two camps. One camp says it's definitely a comet. Anyone who suggests otherwise is peddling pseudoscience, and we don't need to seriously consider alternative explanations because we already know the answer. The other camp says we should remain open to all possibilities, collect as much data as possible, and let the observations tell us what's real rather than deciding in advance based on what we're comfortable believing. The first camp has the numbers. Most astronomers agree that 3I-ATLAS is almost certainly a comet. Most press releases describe it as a comet. Most public communication treats the matter as settled. And for the vast majority of cases, that's the right approach. Most interstellar objects will be natural. Most comets are just comets. Jumping to extraordinary conclusions without extraordinary evidence is bad science. But the second camp has a point too. The evidence for 3I-ATLAS being a normal comet is weaker than the confident pronouncements suggest. The anomalies are real. The statistics are troubling. The fact that every explanation requires invoking special circumstances, unusual compositions, rare geometries, it starts to feel like the hypothesis is being protected by epicycles rather than supported by data. Cox's dismissal stung because it bypassed the substance entirely. He didn't address the 9 anomalies. He didn't explain why the trajectory alignment is no big deal, or why the nickel abundance is perfectly natural, or why the sunward jet is an optical illusion after all. He just said drivel, and his authority as a public scientist was enough to convince millions of people that Loeb was wrong. Loeb's response was measured but cutting. He didn't attack Cox personally. He didn't question his intelligence or his credentials in particle physics. He simply pointed out that Cox hasn't done the work on this particular problem. He's commenting from the sidelines. He's a spectator, not a player. And in science, the people who do the work, who collect the data, who publish the papers, those are the people whose opinions carry weight. Lintott's role is more subtle but potentially more damaging. As an editor, he has the power to shape what gets published and what doesn't. By pressuring Loeb to remove the technological hypothesis from a paper that was otherwise scientifically sound, He wasn't protecting the integrity of science. He was protecting the comfort of scientists who don't want to deal with uncomfortable questions. This happens more often than the public realizes. Scientific journals have biases, editors have preferences, reviewers have opinions about what constitutes legitimate research and what constitutes fringe speculation. And those biases, those preferences, those opinions, they influence what gets published and what gets rejected. They create a filter that lets certain ideas through and blocks others, not always based on the quality of the data or the rigor of the analysis, but based on whether the conclusion feels acceptable to the community. Loeb has been fighting that filter for years, with Oumuamua, with the search for alien technology, with the Galileo project. He's willing to ask questions that make his colleagues uncomfortable, and he's willing to endure ridicule and professional pushback because he believes the questions are worth asking. He thinks we owe it to ourselves, as a species, to look at the universe without preconceptions, to follow the data wherever it leads, even if it leads somewhere we didn't expect. Cox and Lintott represent the other side of that debate, the side that says we need to be careful, conservative, sceptical of extraordinary claims, the side that worries about public perception, about maintaining credibility, about not giving ammunition to conspiracy theorists and pseudoscience peddlers, the side that sees Loeb's openness to the technological hypothesis as reckless, dangerous, irresponsible. Both sides have a point. Both sides care about science. Both sides want to get the right answer. But they disagree fundamentally about how to get there. And that disagreement, playing out in public on social media and blog posts and press interviews, is exposing a rift in the scientific community that goes deeper than 3I-ATLAS. It's about who gets to ask questions. It's about what kinds of hypotheses are acceptable. It's about whether we're genuinely open to discovering something new, or whether we've already decided what's possible and anything outside those boundaries must be wrong by definition. The irony is that the data will decide, not Cox, not Loeb, not Lintott. The data. When JUICE observes 3I-ATLAS on November 4th, when ground-based telescopes get their shot in mid-November, when Hubble and Webb take their deep exposures in December, the measurements will either support the natural comet hypothesis or they won't. The plume will either be there or it won't. The acceleration will either correlate with observable mass loss or it won't. And when that data comes in, one side will be vindicated and the other will have to explain why they were so confident about the wrong answer. That's science. That's how it works. You make predictions, you test them. You accept the results even if they're not what you wanted. But in the meantime, the fight continues. Cox calling it drivel. Loeb calling out the lack of published research. Lintott trying to edit away the uncomfortable hypotheses, and millions of people watching trying to figure out who to trust, who to believe, who's doing real science and who's just chasing headlines. The answer, frustratingly, is that they're all doing real science, just with different priorities and different tolerances for uncertainty. Cox wants to protect the public from false hope and wild speculation. Lintott wants to maintain standards and prevent the journals from becoming platforms for unvetted ideas. Loeb wants to make sure we don't miss something important because we were too scared to look. November 4th. 4 days. The first new data will start arriving. And after that, the argument becomes less about personalities and more about facts. Less about who has the right to ask questions and more about what the answers actually are. One way or another, 3I-ATLAS is going to settle this debate. Not by proving anyone definitively right or wrong, but by providing evidence that's clear enough, strong enough, unambiguous enough that both sides have to acknowledge it. And until then, the scientific civil war rages on, played out in tweets and blog posts and papers and press releases, while a 5-kilometre-wide object hurtles through space, completely indifferent to the human drama unfolding in its wake. Perihelion, the perfect hiding spot. October 29th, 11:47 Universal Time, perihelion. The moment 3I-ATLAS reached its closest distance to the Sun, 203 million kilometres, positioned perfectly between the orbits of Mars and Earth. For a natural comet, this is just geometry. For a spacecraft, this is the golden moment. The Oberth effect is one of the most elegant principles in astronautics. When you're deep in a gravity well, when you're moving at your fastest orbital velocity, any thrust you apply gets amplified. The kinetic energy you already possess multiplies the effectiveness of your engine burn. It's counterintuitive at first. You'd think it wouldn't matter when you fire your rockets. A given amount of propellant produces a given amount of delta V, right? But that's not how orbital mechanics works. The energy you gain from a burn depends not just on the thrust itself, but on the velocity you have when you apply it. Imagine you're riding a bicycle down a steep hill. You're already going fast. Now you start pedaling. Every push on the pedals adds to your existing speed, and because you're already moving quickly, that addition translates into a much larger increase in kinetic energy than if you'd pedaled the same amount while moving slowly. The Obert effect is the same principle, scaled up to spacecraft traversing gravity wells. For 3I-ATLAS, perihelion is the bottom of the gravity well, the point where solar gravity has accelerated it to maximum speed, the point where any additional thrust, any course correction, any velocity change produces the biggest impact on the final trajectory. If you're going to maneuver, if you're going to adjust your path through the solar system, this is when you do it. Not earlier, not later, right here, right now. And that's exactly when the non-gravitational acceleration was measured. Coincidence? Maybe. Comets do tend to be most active at perihelion. The solar flux is highest, the temperature is highest, sublimation rates peak. If 3I-ATLAS is a comet, it makes sense that we'd see the strongest outgassing effects right around closest approach. All the models predict this, all the observations of other comets confirm it. But here's the uncomfortable detail. The timing is too perfect. Not just close to perihelion, but at perihelion. Not a few days before, not a few days after, but right at the moment when an Oberth maneuver would be most effective. The odds of natural outgassing ramping up to produce measurable acceleration at exactly the optimal moment for gravitational assist are, well, low. Not impossible. Nature doesn't schedule its processes to align with human engineering principles, but low enough to make you pause, low enough to make you wonder. And then there's the other detail, the one that makes the whole thing feel less like coincidence and more like design. 3I-ATLAS reached perihelion while Earth was on the opposite side of the Sun. Solar conjunction. From our perspective, the comet and the Sun occupied nearly the same position in the sky, separated by less than 3 degrees. You can't observe an object that close to the Sun with ground-based telescopes. The daylight drowns everything out. Even observations shortly after sunset or before dawn become impossible when the target is within about 15 degrees of the Sun. From October 21st to November 14th, 3I-ATLAS is effectively invisible from Earth. 24 days, nearly a month, right when it's most active, right when the most interesting physics is happening, right when any anomalous behaviour would be easiest to detect. Was this trajectory planned? Did something calculate the optimal path through the inner solar system, one, that would bring it close to the Sun for a gravitational assist while simultaneously positioning it behind the Sun, as seen from Earth during the critical manoeuvring window? The mathematics aren't trivial, but they're not impossible either. If you know where Earth is going to be, and you know where the Sun is, and you have control over your trajectory, you can thread the needle. You can arrange to pass perihelion on the far side of the Sun relative to Earth's position. It's the sort of thing mission planners do all the time for solar observation spacecraft that need to avoid Earth's radio interference during key measurements. 3I-ATLAS didn't need to avoid Earth's radio interference. But if it wanted to avoid Earth's optical telescopes during a critical burn, solar conjunction would accomplish that perfectly. Here's what we do know about what happened during perihelion. The space-based coronagraphs saw it. Stereo A was positioned about 47 degrees ahead of Earth in its orbit, so from Stereo's perspective, 3I-ATLAS wasn't behind the Sun. It was off to the side, visible in the fields of view of both the Cortu coronagraph and, earlier in September, the HI-1 heliospheric imager. SOHO sits at the Earth-Sun L1 point, always between Earth and the Sun, and its LASCO C3 instrument caught 3I-ATLAS in mid to late October as the comet crossed through the coronagraph's field of view. GOES 19, in geostationary orbit around Earth, had a similar but slightly different vantage point, and its CCOR-1 camera captured the comet between October 18th and 24th. 4 instruments, 4 different locations, all of them designed to study the Sun, not comets, but all of them capable of detecting bright objects that happened to pass through their fields. And all of them recorded 3I-ATLAS during the perihelion passage that was supposedly hidden from observation. So we do have data, not high-resolution imaging, not detailed spectroscopy, not the kind of observations you'd get from a dedicated telescope, tracking the comet continuously with optimized filters and integration times. But enough to see the brightness, measure the photometry, detect the extended coma, confirm that the object was there and was active. What the coronagraphs couldn't see, was fine detail. They didn't resolve the nucleus. They didn't image any discrete structures, any fragments breaking away, any jets erupting from specific regions of the surface. The spatial resolution just isn't good enough. CCOR1, with its 19 arcsecond pixels, can barely resolve the comet as extended versus point-like. LASCO C3 is even coarser at 56 arcseconds per pixel. These instruments are built to image the solar corona, enormous structures millions of kilometers across. A 5-kilometer nucleus is microscopic by comparison. So we know 3I-ATLAS brightened. We know it developed an extended coma. We know its color shifted blue, but we don't know if it fragmented. We don't know if its rotation changed. We don't know if any discrete structures appeared that might indicate venting from specific locations, rather than uniform sublimation across the whole surface, and that's frustrating. Because those details matter. A natural comet undergoing thermal stress at perihelion might fracture. The ice holding the nucleus together weakens as temperature rises. Thermal expansion creates stresses. Rapid outgassing can blow chunks off the surface. It's not uncommon. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before crashing into Jupiter. Comet Schwarzmann-Wachmann 3 split into dozens of pieces during a close solar pass. Fragmentation is a normal expected outcome when comets get too close to the Sun and the structural integrity can't handle the heating. If 3I-ATLAS fragmented, the coronagraphs might not have been able to tell. The fragments would be close together initially, still within the same patch of sky, still unresolved as individual objects. Only later, as the fragments separated along slightly different trajectories, would they become distinct, and that separation would take days or weeks to become obvious. If 3I-ATLAS didn't fragment, if it held together through 770 watts per square meter of solar irradiation, while losing billions of tons of mass to sublimation, then it's either unusually strong for a comet nucleus, or it's not losing as much mass as the acceleration implies. Both options are problematic for the natural explanation. Comet nuclei aren't known for structural strength. They're rubble piles, loosely bound aggregations of ice and rock held together by weak gravity and the cohesion of frozen volatiles. Heat them up, let the ices evaporate, and the whole thing tends to fall apart. The fact that 3I-ATLAS might have survived perihelion intact, assuming it did, suggests either an unusually robust structure or a composition that doesn't match typical comets. Or it suggests that the object isn't held together by ice and gravity at all, that it has structural integrity from something else, something manufactured, something designed to withstand thermal stress and mechanical loads without disintegrating. We'll find out soon enough. When 3I-ATLAS emerges from behind the Sun in mid-November, ground-based telescopes will get their first good look at the post-perihelion state. If it fragmented, we'll see multiple objects where there used to be one. If it didn't, we'll see a single nucleus, possibly larger or smaller than before depending on how much mass was lost, but still intact, still coherent, still travelling along its trajectory. JUICE will see it first, November 4th. The European Space Agency's Jupiter Icy Moons Explorer is currently on its way to the outer solar system, carrying a suite of cameras and spectrometers designed to study Europa, Ganymede, and Callisto, the large icy moons where subsurface oceans might harbour life. JUICE wasn't built to study comets, but it has cameras, and 3I-ATLAS will pass within 64 million kilometres of the spacecraft's position. 64 million kilometres sounds far, but in astronomical terms it's close. Close enough for JUICE's instruments to resolve the coma, measure brightness, collect spectra if the comet is bright enough. The geometry is excellent. The solar elongation from JUICE's perspective is over 18 degrees, far enough from the sun's glare that observations are feasible. And unlike Earth-based telescopes, JUICE won't have to wait for twilight or work around atmospheric turbulence. It's in space, with a clear view, at a moment when 3I-ATLAS should still be active if the perihelion heating triggered significant sublimation. What JUICE sees will constrain the possibilities. If the coma is massive, if the brightness is still high, if spectral lines indicate ongoing gas production at rates consistent with the calculated mass loss, then the natural comet hypothesis gained support. The acceleration was from outgassing, just like we thought, and the object is behaving as expected for a volatile-rich nucleus near perihelion. If the coma is compact, if the brightness has dropped off faster than sublimation models predict, If there's no sign of the billions of tons of gas that should be surrounding the nucleus, then we have a problem. Then the acceleration isn't explained by outgassing, and we need a different mechanism. And the list of alternative mechanisms is short, disturbingly short. There's also the question of what happened to the trajectory. Did it change? The 4 arcsecond deviation measured by ALMA on October 29th tells us there was acceleration. But acceleration over a short period doesn't necessarily mean a major trajectory change. It depends on the magnitude, the duration, the direction. Small thrusts applied briefly might nudge the orbit slightly without dramatically altering the path. Larger thrusts, or sustained burns, would produce noticeable changes. JPL updates their orbital elements regularly as new observations come in. The current ephemeris for 3I-ATLAS, orbit number 27, incorporates the non-gravitational acceleration parameters that Nokia filed. Those parameters describe how much the trajectory deviates from pure gravity. As more data arrives, from JUICE, from ground telescopes, from Hubble and Webb, JPL will refine the orbit, update the non-gravitational terms, and we'll see whether the acceleration was a brief spike or a sustained effect. If it was brief, if the acceleration only lasted a few hours or days around perihelion, then it might have been a response to peak solar heating. A burst of sublimation, intense but short-lived, producing thrust for a limited time before the outgassing dropped back to lower rates. That would be consistent with natural comet behaviour, albeit on the extreme end. If it was sustained, if the acceleration continued for weeks before and after perihelion, then we're looking at something more controlled, more deliberate, less like a comet passively responding to thermal input, and more like a craft actively adjusting its course. The data will tell us. JPL's orbit fits will tell us. The December 19th close approach to Earth will provide precise astrometry that can be compared to the pre-perihelion observations, and any deviation from the predicted path will show up clearly. You can't hide trajectory changes. Orbital mechanics is too precise. If 3I-ATLAS manoeuvred, we'll know, but for now, we're in the gap, the observational gap, the 24 days when the most important object in the solar system is hiding behind the sun, doing whatever it's doing invisible to the telescopes that could tell us what's real and what's speculation. 4 days until JUICE, 14 days until ground-based telescopes can see it again, 49 days until the closest approach to Earth when every major observatory will be pointed at 3I-ATLAS, collecting data, measuring positions, comparing observations to predictions. 49 days to find out if perihelion was just a routine passage through the inner solar system, or if it was the moment when something from another star executed a carefully planned gravitational assist, using our sun's mass to alter its trajectory in ways we're only beginning to understand. The perfect hiding spot, whether by chance or by design. And soon, very soon, we'll know which. The missing mass cloud. 5.5 billion tons of gas. That's not a metaphor. That's not an approximation. That's the minimum amount of material 3I-ATLAS must have ejected during its perihelion passage if the non-gravitational acceleration came from sublimation. 5,500 million tons. Written out, that's 5.5 times 10 to the power of 15 grams, 5.5 petrograms, the mass of about 50 billion average-sized automobiles, or a cube of ice roughly 2 kilometers on each side. Gone, vaporized, blown into space by solar heating, spreading outward from the nucleus at hundreds of meters per second, forming a cloud that should be visible from Earth, from Mars, from every spacecraft with a camera pointed in the right direction. Except we haven't seen it yet. And that's becoming a problem. The calculation is straightforward. Avi Loeb walked through it on October 30th, the day after perihelion, and anyone with a background in physics can verify the numbers. Momentum must be conserved. When gas molecules leave the surface of a comet nucleus, they carry momentum away. That momentum has to come from somewhere. It comes from the nucleus itself, which recoils in the opposite direction, like a rocket engine expelling exhaust. The mass times acceleration of the nucleus equals the rate of mass loss times the velocity of the ejected gas. Rearrange the equation and you get the evaporation timescale. The time it takes to lose a significant fraction of the nucleus mass. For 3I-ATLAS, with the acceleration for Nokia measured, that timescale is about 6 months. 6 months to lose half the mass. 1 month to lose 1/6. 1/6 of 33 billion tons is 5.5 billion tons. That's how much gas should be surrounding 3I-ATLAS right now. Not might be, should be. The physics demands it. If the acceleration is real, and the acceleration is from outgassing, then the gas is there. It has to be. So where is it? The Webb telescope measured a mass loss rate back in the spring, before perihelion, when 3I-ATLAS was still several astronomical units from the Sun. 150 kilograms per second. Steady. Continuous. Over 5 months that added up to billions of kilograms, but spread over such a long time and at such a low rate that it didn't produce a measurable non-gravitational acceleration. The gas drifted away slowly, forming a tenuous coma that spectroscopy could detect, but that didn't overwhelm the reflected sunlight from the nucleus. Now, post-perihelion, the mass loss rate should be vastly higher. The acceleration data implies a rate thousands of times larger than what Webb measured. And at that rate, the gas shouldn't be tenuous anymore. It should be dense, bright, obvious. Think about what 5 billion tons of water vapor looks like in space. Water molecules, H2O, have a molecular weight of 18. That means 5 billion tons corresponds to about 1.7 times 10 to the 32nd molecules. 10 to the 32. 100 million trillion water molecules. If they break down into hydroxyl radicals and hydrogen atoms under solar UV, which they do almost immediately, you get twice as many hydroxyl radicals. 3 times 10 to the 32nd OH molecules, each fluorescing at characteristic wavelengths in the ultraviolet and radio spectrum. Jacques Crovizier's radio observations detected OH production in mid-October. The rate he measured, 5.7 times 10 to the 28th molecules per second, was already high. But that was cumulative production over some averaging time, probably hours or days depending on the radio telescope integration. The total number of OH molecules present in the coma at any given moment depends on the production rate and the photodissociation lifetime, the time it takes for solar UV to break the OH apart into oxygen and hydrogen. At 1 astronomical unit from the Sun, OH has a lifetime of about 160,000 seconds, roughly 2 days. Close to the Sun, the lifetime drops. At 3I-ATLAS's perihelion distance of 1.36 AU, the lifetime is somewhat shorter, maybe 140,000 seconds. Still long enough that if OH is being produced at 10 to the 28th molecules per second, a steady-state coma builds up containing about 10 to the 33rd molecules at any given time. That's a cloud. Real, massive, detectable cloud of hydroxyl radicals fluorescing under solar UV, emitting photons, scattering light, creating a visible halo around the nucleus. Radio telescopes should see it easily. Optical telescopes with the right filters should see it too. UV spectrographs should detect absorption or emission lines. It's not subtle. It's not marginal. It's billions upon billions of molecules screaming their presence into the electromagnetic spectrum. And yet, as of October 30th, we don't have confirmation that it's there at the scale the acceleration predicts. We have Crovizier's measurement from mid-October, but that was before perihelion, when the object was slightly farther from the Sun and presumably less active. We don't have post-perihelion OH measurements yet. The radio telescopes haven't published updated observations. The ground-based optical telescopes can't see 3I-ATLAS because it's behind the Sun from Earth's perspective. That's where JUICE comes in, November 4th, 4 days from now. The spacecraft carries several instruments that could detect the coma if it exists. Janus, the optical camera system, can image the comet and measure its brightness and extent. UVS, the ultraviolet spectrograph, can detect OH and other species in the UV. MAJORS, the visible and infrared spectrometer, can measure the composition of the coma gas. If 3I-ATLAS is surrounded by 5 billion tons of sublimated material, JUICE will see it. The geometry is favourable. JUICE will be about 64 million kilometres from 3I-ATLAS, close enough for decent spatial resolution. The solar elongation from JUICE's position is over 18 degrees, far enough that solar glare shouldn't interfere. The phase angle, the angle between the Sun, the comet and JUICE, will be relatively low, meaning JUICE will be looking at the sunlit side of the coma where activity should be strongest. If JUICE's cameras show a large diffuse coma, with an apparent size consistent with billions of tons of gas expanding at hundreds of meters per second, then the mystery is solved. 3I-ATLAS is a comet, an unusual one with extreme activity but still fundamentally natural. The acceleration was from outgassing. The blue colour was from gas emission. The whole thing fits. But if JUICE's images show a compact nucleus with only a faint small coma, inconsistent with the mass loss required to produce the measured acceleration, then we have a major discrepancy. Then the math doesn't work. Then something is accelerating 3I-ATLAS. Without producing the observable signature we expect from sublimation. Loeb put it plainly in his October 30th blog post. If the extensive EON data will not reveal a massive cloud of gas around 3I-ATLAS, then cometary evaporation would not constitute a natural explanation for its non-gravitational acceleration. And if it's not evaporation, then what's left? What other mechanism produces thrust without ejecting mass? Or at least without ejecting enough mass to be detectable? There are very few options. Radiation pressure on a low-density, high-surface area object. But 3I-ATLAS is big, at least 5 kilometers across and presumably dense. Radiation pressure works on things like solar sails, thin films with enormous area-to-mass ratios, not on multi-billion-ton chunks of rock and ice. Solar wind momentum transfer. The solar wind carries charged particles that could, in principle, push against a conductive surface. But the effect is tiny, orders of magnitude too small to explain the measured acceleration. You'd need a magnetic field, some way to couple the solar wind to the object more efficiently. That's possible, but it requires specific conditions that natural comets don't typically have. Or an engine, internal propulsion, a reaction drive burning fuel or expelling reaction mass in a controlled, directed way. Not a rocket in the traditional sense necessarily. Could be ion drive, could be plasma thruster, could be something more exotic, but something that produces thrust without creating a massive visible exhaust plume. That sounds like science fiction. It sounds absurd. And yet, if the gas cloud isn't there, if JUICE comes back with images of a quiet, compact object that's accelerating anyway, then absurd starts looking like the only option left on the table. The dark comet hypothesis tries to bridge this gap. A dark comet, by definition, is an object that undergoes outgassing but doesn't produce a visible coma or tail. The term was invented to explain Oumuamua, which showed non-gravitational acceleration without any detectable gas or dust around it. Spitzer looked, found nothing. So comet experts said, well, maybe the gas is there but it's not producing a visible signature. Maybe the dust-to-gas ratio is so low, or the composition is so unusual, that standard detection methods miss it. Loeb has pointed out the logical problem with this. If you define a comet as an object with a visible coma and tail, then a dark comet is an oxymoron. It's like saying invisible light or silent sound. The coma and tail are the defining features of a comet. Take those away, and you're left with an object that accelerates without visible cause, which sounds a lot like a spacecraft, not a comet. But let's take the dark comet idea seriously for a moment. Suppose 3I-ATLAS is outgassing, but the gas isn't producing the bright coma we expect. How would that work? You'd need the gas to leave the surface quickly without much dust entrained, and you'd need it to be transparent at visible wavelengths. Water fits that description reasonably well. Water vapour is invisible. It doesn't scatter light efficiently. It only becomes visible when it fluoresces under UV, or when dust particles mixed with it scatter sunlight. But OH, the breakdown product of water, does fluoresce. That's what Crozier detected in radio. An OH emission should be visible in UV and at certain optical wavelengths. If there are 10 to the 33rd OH molecules in the coma, they should be emitting photons at a detectable rate. Not as bright as the dust scattering, perhaps, but measurable with good instruments. JUICE has good instruments. UVS can detect OH emission. If it's there at the levels the mass loss calculation predicts, UVS will see it. And if UVS doesn't see it, if the OH flux is much lower than expected, then either the mass loss isn't as high as we calculated, which means the acceleration isn't from outgassing, or the water isn't breaking down into OH, which would be bizarre and would require some explanation involving unusual chemistry, or shielding from solar UV. There's another possibility. Maybe the mass loss is real, but it's not water. Maybe 3I-ATLAS is ejecting material that doesn't fluoresce, doesn't scatter light efficiently, doesn't show up in spectra. But what would that material be? Nitrogen? CO? Noble gases? Those don't produce bright emission lines in the visible or UV, but they also don't produce strong thrust. They're light. To get the same momentum transfer, you'd need to eject them at very high velocities, much higher than the thermal speeds expected from sublimation. And that brings us back to some kind of active expulsion mechanism, not passive evaporation. The missing mass cloud is the linchpin. If it's there, the natural explanation survives. If it's not, the natural explanation collapses, and we're left staring at an interstellar object that's doing something comets shouldn't be able to do. Ground-based telescopes will have their chance starting in mid-November. By then, 3I-ATLAS will have emerged from behind the Sun, and observers around the world will point their instruments at it, looking for the coma, measuring the brightness, collecting spectra. The International Asteroid Warning Network has already coordinated a campaign. From November 27th to January 27th, dozens of observatories will track 3I-ATLAS, gathering astrometry to refine the orbit and photometry to characterise the activity. That's almost 2 months of intensive observation. If the coma is there, if the gas is present at the levels required by the acceleration, the campaign will document it. Multiple independent teams, multiple instruments, multiple wavelengths. No ambiguity, no controversy. The data will be clear. And if the data shows a faint coma, much smaller than predicted, with gas production rates that don't match the momentum requirements, then every observatory in that campaign will have contributed to one of the most significant findings in the history of astronomy. The confirmation that an interstellar object is capable of non-gravitational acceleration without the observable mass loss that such acceleration should produce. December 19th is the big one. Closest approach to Earth, 269 million kilometres, still far by everyday standards, but close enough that Hubble can resolve details, Webb can collect high-resolution spectra, ground-based telescopes can measure positions with sub-arc-second precision. The geometry is excellent. The observing conditions are as good as they'll ever be for this object. If 3I-ATLAS is surrounded by a massive gas cloud at that point, we'll see it. The cloud should be even larger than at perihelion because the gas has had more time to expand. Sublimation might have slowed down as the object moved away from the Sun, but the gas already released would still be there, spreading outward, forming a coma hundreds of thousands or even millions of kilometres across. Hubble's cameras would capture it easily. Webb's NIRS-SPEC could dissect the composition, identify the molecular species, measure their abundances, compare to solar system comets, and to theoretical models of interstellar chemistry. But if Hubble images show a compact object, if Webb spectra show weak gas lines inconsistent with billions of tons of ejected material, if the astrometry confirms that the non-gravitational acceleration continued post-perihelion without the corresponding mass loss, then we have proof. Not speculation, not hypothesis. Proof that 3I-ATLAS is not behaving like a natural comet. The missing mass cloud will either be found or it won't. There's no middle ground. The physics is too clear. The predictions are too specific. 5.5 billion tons, that's the number. And in the next few weeks, every major telescope in the solar system will be looking for it, measuring it, trying to confirm or rule out its existence. 4 days until JUICE, the first test. The first real chance to see if the gas is there. And if it's not, if JUICE comes back with images that don't show the expected coma, then we brace ourselves for what comes next. Because an object that accelerates without visible exhaust is not following the rules we've spent centuries learning. It's doing something else, something we need to understand, something that might be the most important discovery humanity has ever made, or the most unsettling question we've ever had to confront. The missing mass cloud. Either it's there, scattered across millions of kilometres of space, glowing faintly under solar radiation, waiting to be detected, or it's not, and if it's not, then everything changes. Anomaly. Stack now at 9. The non-gravitational acceleration is anomaly number 9. Not the first oddity, not even the strangest. Just the latest in a growing list of properties that make 3I-ATLAS unlike anything we've seen before. And when you stack anomalies, when you multiply their probabilities together, the cumulative odds become staggering. 1 in 10 quadrillion. That's Loeb's estimate for the combined probability of all 9 anomalies occurring naturally in a single object. 1 in 10 to the 16th. Written out, that's 1 in 10 million billion. Those aren't lottery odds. Those aren't even cosmic accident odds. Those are numbers. So small they start to challenge the idea that we're looking at a random collection of natural circumstances. Let's walk through them. All 9, one by one. Anomaly 1. Trajectory alignment with the ecliptic plane. 3I-ATLAS's orbital plane is tilted by only 5 degrees relative to the ecliptic, the plane in which Earth and the other planets orbit the Sun. Most interstellar objects should arrive from random directions. The galaxy is three-dimensional. Stars are scattered throughout the disk and halo. An object ejected from a planetary system light years away should have no particular alignment with our solar system's architecture. The probability of arriving within 5 degrees of the ecliptic by chance, about 0.2%, 1 in 500. Anomaly 2. The sunward jet. Between July and August, 3I-ATLAS displayed an anti-tail, a structure pointing toward the sun rather than away from it. Anti-tails can be optical illusions, perspective effects, when you're viewing a curved dust tail from just the right angle. But careful analysis of the geometry showed this wasn't perspective. The structure was real. It pointed sunward. Comets don't do that. Pressure from solar radiation and the solar wind pushes material away from the sun, always. A sunward jet requires some other force, some mechanism that ejects material in a direction opposite to the expected flow. The paper documenting this found it to be inconsistent with known cometary behaviour. Anomaly 3. Nucleus mass. 3I-ATLAS is huge compared to other interstellar objects, at least 5 kilometres in diameter, possibly larger. Mass estimates put it at 33 billion tonnes or more. That's about 1 million times more massive than Oumuamua and 1,000 times more massive than Borisov, and it's moving faster than both. Kinetic energy scales with mass times velocity squared. A large, fast object carries enormous energy, and the probability of detecting such an object so soon after we started looking for interstellar visitors is very low. Less than 0.1%, according to population models. Anomaly 4. Water depletion. The gas plume detected by the Webb telescope and other observatories contained only 4% water by mass. 4%. Most solar system comets are more than 50% water ice. Some are much higher. Water is the dominant volatile in the outer solar system because it's abundant in molecular clouds, the regions where stars and planets form. A comet with only 4% water is extremely unusual. It suggests either a very different formation environment or significant processing that removed the water. Anomaly 5. Extreme negative polarization. Polarization measures how light waves are oriented after scattering off a surface. Most objects show positive polarization, meaning the reflected light waves tend to align, perpendicular to the scattering plane. 3I-ATLAS showed extreme negative polarization, unprecedented for any known comet including Borisov. The probability of this occurring naturally based on comparisons to thousands of other measurements is less than 1%. Negative polarization can happen, but extreme negative polarization is rare and requires specific surface properties that most comets don't have. Anomaly 6. The WOW signal correlation. In 1977, the Big Ear radio telescope in Ohio detected a strong narrow band signal from the direction of the constellation Sagittarius. The signal lasted 72 seconds, rose and fell in intensity consistent with the telescope's beam pattern, and was never detected again despite numerous follow-up attempts. It's called the WOW signal, named after the exclamation astronomer Jerry Eman wrote in the margin of the printout when he saw it. The signal's origin remains unknown. Could have been terrestrial interference, could have been an astrophysical transient, could have been something else. 3I-ATLAS, when its trajectory is traced backward, came from a direction within 9 degrees of the WOW signal's origin. 9 degrees on the sky. The probability of an interstellar object arriving from within 9 degrees of any specific point. About 0.6%, 1 in 167. Not impossible. The sky is full of directions, but combined with everything else, it's another data point that doesn't fit the random arrival hypothesis cleanly. Loeb has been careful not to overclaim this connection. He's stated multiple times that the WOW signal was almost certainly not from 3I-ATLAS directly. The signal was detected 48 years ago, and 3I-ATLAS was much farther away at that time. If the object were transmitting at radio wavelengths strong enough to be detected across interstellar distances, we'd have picked up the signal again by now, multiple times from multiple telescopes. The fact that we haven't means either it wasn't transmitting, or it stopped, or the signal was a one-time burst. But the directional coincidence is curious. If 3I-ATLAS came from a system in that region of the galaxy, and if that system harboured a technological civilization, and if that civilization sent both a radio beacon and a physical probe toward nearby stars, then arriving from the same direction makes sense. Not proof, not even strong evidence. just an interesting alignment that raises questions worth asking. Anomaly 7. Nickel without iron. Spectroscopy in July and August revealed strong nickel emission lines in the coma. Nickel, the element, atomic number 28. Not nickel compounds, not nickel mixed with other metals. Pure nickel vapour, detected at a distance of over 4 astronomical units from the Sun, where temperatures should be far too cold for metal sublimation. And the abundance was high, much higher than iron, which is normally more abundant than nickel in cosmic material, by a factor of about 20 to 1. 3I-ATLAS showed nickel, but very ATLAS showed little iron. The ratio was inverted, backwards, wrong. Comet experts have suggested that perhaps the nickel is bound in volatile molecules like nickel tetracarbonyl, which sublimes at lower temperatures. But that's a speculative explanation, not confirmed by observation, and it requires unusual chemistry that we don't fully understand. Anomaly 8. Rapid brightening. The photometry from STEREO, SOHO and GOES documented brightness, increasing with heliocentric distance to the power of negative 7.5. Oort cloud comets typically show exponents between 2 and 4. Exponents above 6 are almost unheard of. The paper states plainly that the reason for this rapid brightening remains unclear and far exceeds typical behaviour. It's possible the object has unusual volatile content, or unusual structure, or unusual thermal properties. Possible, but not yet demonstrated. Just another anomaly requiring ad hoc explanations. Anomaly 9. Non-gravitational acceleration. 4 arcseconds off the predicted position. Measurable thrust. Momentum requiring billions of tons of ejected gas. We've covered this. It's real, it's documented, and it's the capstone of the anomaly stack, the one that pushes the whole situation from interesting to urgent. Now multiply the probabilities. Not literally, because some of these anomalies might be correlated. If the object has unusual composition that could explain both the nickel abundance and the water depletion. If it's structurally strong, that could explain both the large mass and the survival through perihelion heating. You can't just multiply independent probabilities if the events aren't independent. But even accounting for correlations, even being generous with the estimates, the cumulative probability is tiny. Loeb's calculation yields less than 1 part in 10 to the 16th. 1 in 10 quadrillion. That's the odds that all 9 of these features would occur together in a single natural object arriving from interstellar space. To put that in perspective, there are roughly 10 to the 11 stars in our galaxy. 100 billion stars. If each star ejected 1 interstellar object over its lifetime, and those objects were distributed randomly, the probability of finding one with all 9 of 3I-ATLAS's anomalies in our immediate neighbourhood is effectively 0. You'd expect to find one such object across many galaxies, not in our own solar system within 5 years of starting to look for interstellar visitors. Does this prove 3I-ATLAS is artificial? No. Probability arguments don't prove anything. Low probability events happen all the time. Every specific sequence of coin flips is fantastically unlikely if you calculate the odds beforehand, but one of those sequences has to occur. Somebody wins the lottery even though the odds are astronomical. Rare things are rare, not impossible. But probability arguments do tell you where to focus your attention. When you see a clustering of low probability events, when multiple independent anomalies align in a single object, that's a signal. It might be noise, it might be coincidence. But it's worth investigating seriously, not dismissing out of hand. The 9 anomalies aren't secrets. They're published, documented, available for anyone to check. The raw data is in archives. The calculations are in papers. The logic is transparent. If there are errors, other scientists can find them, point them out, publish corrections. That's how science works. Claims get scrutinized and mistakes get caught. Weak arguments get exposed. So far the anomalies have held up. Individual explanations have been proposed for some of them. Maybe the trajectory alignment is just luck. Maybe the nickel comes from tetracarbonyl. Maybe the rapid brightening is due to CO2-dominated composition, switching to water ice, dominated as temperature rises. Each anomaly, considered alone, can be explained away with some combination of unusual but not impossible circumstances. But all of them together? That's where the cumulative improbability becomes hard to ignore. Every explanation is a special case. Every anomaly requires invoking rare conditions. At some point, the stack of rare conditions becomes less plausible than the alternative hypothesis. The hypothesis that these aren't separate coincidences but connected features of an object whose nature we've misidentified. Loeb developed a quantitative scale to assess this. The Loeb scale, running from 0 to 10. 0 means definitely natural. 10 means definitely technological. The scale incorporates multiple lines of evidence, weights them by reliability and significance, and outputs a score representing how consistent the observations are with each hypothesis. 3I-ATLAS ranks at 4 on that scale. Not 0, not 10. 4. Ambiguous. Uncertain. Right in the middle of the range where we can't dismiss either possibility based on current data. Below 5, the natural hypothesis is more likely. Above 5, the technological hypothesis gains ground. At 4, we're at the tipping point. One or two more anomalies, or stronger confirmation of existing ones, could push it higher. Alternatively, finding natural explanations that account for multiple anomalies simultaneously could push it lower. The scale isn't perfect, it's not a proof. It's a framework for thinking about the problem quantitatively instead of relying on gut feelings or rhetorical arguments. And right now, that framework says we can't be certain. We need more data, which brings us back to November and December, the missing mass cloud, the post-perihelion observations, the close approach to Earth. Every piece of data we collect will either support the natural hypothesis by showing that the anomalies have conventional explanations, or support the alternative by demonstrating that the anomalies persist and intensify under scrutiny. The WOW signal connection is the most speculative anomaly on the list. It's easy to dismiss. 9 degrees on the sky covers a lot of area. Thousands of stars fall within that cone. The odds of any given interstellar object arriving from somewhere in that region are low, but not infinitesimal. And we have no proof that the WOW signal had anything to do with intelligent transmission. It could have been glitch. It could have been interference. It could have been a natural astrophysical phenomenon we don't understand yet, but it lingers. Because the WOW signal was unique. In 50 years of SETI observations scanning millions of stars detecting billions of signals, nothing else has looked like it. Nothing else had that combination of narrow bandwidth, high intensity and celestial origin consistent with an extraterrestrial source. Most SETI detections are quickly identified as satellites, radar, terrestrial broadcasts. The WOW signal wasn't. It remains unidentified. If 3I-ATLAS is natural, the directional correlation is meaningless, just coincidence. One of many possible directions it could have come from, and it happened to come from the same part of the sky where we once saw something unusual. So what? The universe is big. Coincidences happen. If 3I-ATLAS is not natural, the correlation becomes interesting. Not proof, but interesting. A hint that maybe, possibly, the WOW signal and the object are connected. Maybe the signal was a beacon. Maybe it was part of a network. Maybe it was something else entirely but coming from the same source. Or maybe not. Maybe the object is artificial but has nothing to do with the WOW signal. Those are separate questions. Radio telescopes are monitoring 3I-ATLAS now. Loeb confirmed in his blog post that he's asked observers to check for transmissions. If the object is broadcasting at radio wavelengths, we'll detect it. The sensitivity of modern arrays is extraordinary. If there's a signal, even a weak one, we'll pick it up. And if we do, if 3I-ATLAS suddenly starts transmitting at radio frequencies in patterns that couldn't be mistaken for natural emissions, then the anomaly stack doesn't matter anymore. Then we have direct proof. Then every other question becomes secondary to the immediate reality that we're receiving a message from a technological artifact not built by human hands. But that's speculation. Wishful thinking, maybe. The more likely scenario is silence. No radio signals, no laser flashes, no unambiguous technological signatures. Just the 9 anomalies, stacking up, waiting for explanations that don't require invoking special circumstances for every single feature. The data will decide. November 4th, JUICE's observations, mid-November, ground-based telescopes, December 19th, Hubble and Webb. Each round of observations will either confirm the anomalies or resolve them. Each measurement will either push the Loeb scale score higher or lower. Right now, we're at 4, ambiguous, uncertain, the most honest position given what we know, and in a few weeks, we'll know more, maybe a lot more. The anomaly stack is real. The cumulative probability is calculated. The question is no longer whether 3I-ATLAS is strange. It's whether strange equals unprecedented natural phenomena, or whether it equals something else. something we've been looking for in one form or another for as long as we've wondered if we're alone. December 19th, the Christmas question. 269 million kilometres. That's the distance between Earth and 3I-ATLAS on December 19th, 2025. About 1.8 astronomical units, roughly the distance from Earth to Mars when the planets are on opposite sides of their orbits. Far by everyday standards, close enough that every major telescope on Earth and in space will have a clear shot. 6 days before Christmas. Avi Loeb phrased it deliberately. Will 3I-ATLAS send mini-probes towards Earth as Christmas gifts to humanity? He's not predicting it. He's not claiming it's likely. He's raising the possibility, the scenario that becomes plausible if the object isn't natural, if perihelion was a manoeuvring opportunity, if the trajectory was designed rather than random. The physics of mini-probes is straightforward. If 3I-ATLAS is a mothership, if it's carrying smaller vehicles or instruments, the optimal time to release them is during perihelion. The deep gravity well provides energy. A small delta V applied at perihelion translates into a large trajectory change later. You can aim probes at different planets, different destinations throughout the solar system, using the Sun's gravity to bend the paths into the desired configurations. Earth is one of the obvious targets. If an interstellar mission wanted to study our solar system, Earth would be high on the list. It's the only planet with detectable biosignatures, oxygen in the atmosphere, water on the surface, chlorophyll's spectral signature in reflected light, radio emissions from our technological civilization. Earth stands out. It's interesting. It's worth investigating. Launching a probe from 3I-ATLAS toward Earth during perihelion wouldn't require much thrust. The object's perihelion distance was 1.36 AU. Earth's orbit is at 1 AU. The difference is small. A velocity change of a few hundred meters per second could shift a probe's trajectory from following 3I-ATLAS's hyperbolic path to intersecting Earth's orbital path at a later date. December 19th is 51 days after perihelion. In 51 days, travelling at an average velocity of a few tens of kilometres per second, a small probe could cover the distance from 3I-ATLAS's perihelion location to Earth. Not comfortably, not with a huge margin, but feasibly. The timing works. Loeb isn't saying this is happening, he's saying it's a scenario worth monitoring for. The Galileo project has 3 observatories, Harvard, Colorado, California, each equipped with cameras and sensors, designed to detect anomalous objects in Earth's atmosphere and near-Earth space. They're calibrated, they're automated, they run continuously, collecting data, flagging anything that doesn't fit the pattern of known aircraft, satellites, meteors, or astronomical objects. If mini-probes arrive in December, if they enter Earth's vicinity and begin manoeuvring or transmitting or doing anything detectable, the Galileo observatories might see them. That's the idea. Not to search the entire sky, which would be impossible with 3 ground-based stations, but to monitor systematically and hope that if something unusual is happening, it shows up in the field of view. The December 19th close approach is significant for other reasons too. This is when ground-based telescopes will have their best chance to observe 3I-ATLAS in detail. The object will be moving away from the Sun, receding along its hyperbolic trajectory, but still close enough to Earth that large apertures can resolve structure, measure photometry, collect spectra with high signal-to-noise ratio. Hubble will observe. The Space Telescope Science Institute has already scheduled time. Hubble's cameras can image 3I-ATLAS with resolution good enough to see the nucleus, measure the coma size, detect any fragmentation or asymmetry. The Wide-Field Camera 3 can collect spectra from ultraviolet through near-infrared, covering the wavelengths where gas emission lines appear, where dust scattering dominates, where the comet's colour and composition reveal themselves. Webb will observe too. The James Webb Space Telescope, with its massive 6.5-metre mirror and infrared sensitivity, can penetrate dust that optical telescopes struggle with. Webb's NIRSPEC instrument can dissect the molecular composition of the coma, identifying individual species, measuring their abundances, comparing the ratios to solar system comets, and to theoretical predictions for interstellar chemistry. If there's anything unusual about the gas, anything that doesn't fit standard cometary composition, NIRSPEC will find it. Ground-based telescopes from around the world will participate. The International Asteroid Warning Network coordinated campaign runs from November 27th through January 27th, encompassing the December 19th close approach. Dozens of observatories, professional and amateur, equipped with everything from small backyard telescopes to the 10-metre giants like Keck and the Very Large Telescope, will track 3I-ATLAS, measure its position, record its brightness, collect as much data as possible. This is planetary defence training. OASM treats every close-approaching object as an exercise, a chance to practice the coordination and communication that would be necessary if a real threat were identified. 3. The Atlas isn't a threat. Its trajectory passes nowhere near Earth's orbit. But it's an opportunity. A rare interstellar visitor, observable for months, providing a test case for how the global astronomical community responds to unusual objects. The astrometry will be critical. Precise position measurements, taken from multiple observatories on multiple nights, allow JPL to refine the orbit to extreme accuracy. Any deviations from the purely gravitational path will show up clearly. If 3I-ATLAS manoeuvred post-perihelion, if the non-gravitational acceleration continued or changed direction, the astrometry will reveal it. You can't hide trajectory changes when you have hundreds of precise measurements spread over weeks. And if the trajectory shows continued acceleration, sustained thrust, deviations that correlate with specific events or times, that's evidence of control. That's evidence of something actively adjusting the path rather than passively responding to solar heating. Natural outgassing can produce thrust, but it's messy, variable, dependent on local conditions on the nucleus surface. Controlled thrust is smooth, predictable, directed. The astrometry will distinguish between them. December 19th is also when the brightness measurements will be most telling. If 3I-ATLAS is a comet that lost billions of tons of mass at perihelion, its brightness should be dropping rapidly as it moves away from the Sun. The sublimation rate declines with distance. The coma disperses, the dust settles. Active comets fade after perihelion, sometimes dramatically, as the energy driving their activity decreases. But if the brightness plateaus, if it stays higher than predicted, if it fades more slowly than models expect, that's anomalous. That's consistent with an internal light source, something producing illumination independent of solar heating. Not a strong internal light necessarily, just enough to offset the expected decline, to keep the brightness higher than a passive reflective object should have. The chronograph data already showed blue-shifted light, emission rather than pure reflection. If that continues post-perihelion, if Webb and Hubble and ground-based spectrographs detect gas emission lines at intensities that don't correlate with distance from the Sun, that supports the hypothesis of activity driven by something other than solar flux. Alternatively, if 3I-ATLAS fades quickly, if the coma dissipates, if the spectra show declining gas production consistent with cooling as the object recedes, that supports the natural comet hypothesis. Comets turn off. They run out of volatile material near the surface. The remaining ice gets buried under a lag deposit of dust and refractory material. Activity ceases. The object becomes inert, a dark chunk of rock and depleted ice drifting through space. Which will it be? We'll know by the end of December. The observations are scheduled, the data will arrive. And when it does, the debate shifts from speculation to evidence-based analysis. Loeb's Christmas Gifts comment is provocative. It's designed to make people think about the full range of possibilities. If 3I-ATLAS is a mothership, if it released probes at perihelion, where would those probes go? What would they do? How would we detect them? The simple answer is we don't know. We've never encountered alien technology before. We have no empirical basis for predicting what it would look like, how it would behave, what signatures it would produce. We can only reason from principles, from physics, from the constraints that govern all material objects regardless of who built them. A probe maneuvering in space needs propulsion. Propulsion requires energy and reaction mass, or some equivalent like solar sails using photon pressure. If the probe is small, a few meters or less, it could be hard to detect optically unless it's very close. But if it's maneuvering, if it's changing velocity, it might produce exhaust, heat, electromagnetic emissions. Things that telescopes and radar systems could pick up if they're looking in the right place at the right time. The Galileo project isn't the only entity monitoring. The Space Surveillance Network, operated by the US Space Force, tracks objects in Earth orbit and near-Earth space. They catalogue satellites, debris, anything large enough to pose a collision risk. If a small probe enters cislunar space, the region between Earth and the Moon, the Space Surveillance Network might detect it, depending on its size, reflectivity and trajectory. But detection doesn't mean identification. Small objects get detected all the time. Most turn out to be space junk, fragments of old satellites, rocket stages, debris from collisions. Distinguishing a natural meteoroid from a piece of human-made debris from a hypothetical alien probe requires detailed analysis of the trajectory, the light curve, the radar return characteristics. If something unusual shows up in December, something that doesn't fit the known catalogue, it will get attention, it will get tracked. And if it exhibits controlled motion, if it manoeuvres in ways that rule out natural or human origin, then we'll know. Then the Christmas question gets answered in the most dramatic way possible, but that's the unlikely scenario. The scenario that requires 3I-ATLAS to be not just unusual, but actively engaged in exploration. The more likely scenario is that December 19th comes and goes, Hubble and Webb collect their data, ground telescopes measure positions and brightness, and 3I-ATLAS continues along its trajectory, doing whatever comets do, providing no clear evidence of anything beyond natural phenomena. That would be the expected outcome. The boring outcome. The outcome that confirms our understanding of interstellar objects and lets everyone relax, secure in the knowledge that the universe is mostly rocks and ice, not spacecraft and probes. But boring or not, expected or not, the observations will happen. The data will be collected, and by the end of December, by Christmas, we'll have answers. Not all the answers, not final, definitive proof one way or the other, but enough data to move the needle, to shift the probabilities, to update the Loeb scale score based on real measurements instead of speculation. December 19th, 51 days after perihelion, the closest approach, the moment when Earth gets its best look at the third interstellar visitor ever recorded, and possibly, just possibly, the moment when we find out if we've been looking at a visitor in more than one sense of the word. The Christmas question isn't whether 3I-ATLAS will send gifts. The Christmas question is whether we're ready for the answer, whatever it turns out to be. Whether we're prepared to accept the data even if it contradicts our expectations. Whether we're willing to follow the evidence instead of our preconceptions. Loeb thinks we are. That's why he keeps asking uncomfortable questions, publishing papers that challenge conventional thinking, proposing scenarios that make his colleagues cringe. He believes science works best when it's fearless, when it looks at the universe without flinching, when it accepts that nature might be stranger than we imagined. Brian Cox thinks we need caution. That's why he pushes back, why he labels speculation as drivel, why he emphasizes the natural explanation. He believes science works best when it's disciplined, when it demands strong evidence before accepting extraordinary claims, when it protects the public from false hope and misleading narratives. Both of them care about the truth. Both of them want to understand 3I-ATLAS. They just disagree about the path to get there. December 19th will test both approaches. The data will either vindicate caution, by showing that the anomalies have prosaic explanations, or vindicate curiosity, by showing that the anomalies persist and intensify. Either way, we move forward with more information, less uncertainty, clearer understanding. 50 days, that's all. 50 days until the closest approach. 50 days until the telescopes converge on 3I-ATLAS and extract every photon they can capture. 50 days until we find out if the Christmas question is just a rhetorical device or a genuine possibility that we need to take seriously. And in the meantime, while we wait, 3I-ATLAS keeps moving, 61 kilometers per second, receding from the Sun, carrying whatever it is, whatever it might be, out toward the orbit of Jupiter and eventually beyond. Indifferent to our debates, indifferent to our questions. Just travelling, as it has travelled for billions of years, through the endless dark between the stars. Chapter 8. The Political Dimension. There is a photograph that nobody has seen, a high-resolution image of 3I-ATLAS, captured by the most powerful camera ever sent to Mars, taken at the perfect moment when the interstellar visitor passed within 29 million kilometres of the red planet. The high-rise camera aboard NASA's Mars Reconnaissance Orbiter achieved a pixel resolution of 30 kilometres, meaning that single image could settle some of the most contentious debates about the object's true nature. That photograph exists. It was taken on October 2nd, 2025, and as of today, October 31st, 2025, it remains locked away, unavailable to the scientific community or the public. The reason? A government shutdown that began on October 1st. The same day 3I-ATLAS made its closest approach to Mars, the United States federal government ran out of money. NASA, along with most federal agencies, entered what bureaucrats call a lapse in appropriations. Non-essential personnel were sent home, data releases were suspended, and the HiRISE team, despite having successfully captured potentially the most important astronomical image of the decade, found themselves unable to share their work with the world. This is not supposed to happen. Science, especially time-sensitive observations of objects that will never return, should not be held hostage by political dysfunction. But here we are, watching as partisan budget battles in Washington prevent astronomers from accessing data that could answer fundamental questions about an interstellar visitor. The irony is almost too bitter to process. We have the image. The spacecraft did its job. The camera worked perfectly. But a quirk of American politics means the data might as well not exist. Avi Loeb, never one to stay quiet when he believes science is being compromised, has been vocal about the situation. He finds it unconscionable that crucial observational data could be withheld during such a narrow window of opportunity. 3I-ATLAS will not come back. This is our only chance to study it up close. And while Congress argues over spending bills and shutdown deadlines, the object continues its journey, moving farther from Earth with each passing day, becoming dimmer, harder to observe, slipping back into the cosmic darkness from which it came. Enter Congresswoman Anna Paulina Luna. The representative from Florida's 13th District has emerged as an unlikely champion for transparency in the 3I-ATLAS investigation. Loeb spoke with her directly, updating her on the object's anomalies and the urgent need for the HiRISE data. Luna responded by sending a formal letter to Sean Duffy, NASA's interim administrator, urging the agency to release the images immediately and to consider using the Juno spacecraft near Jupiter to observe 3I-ATLAS during its March 2016-2026 flyby. Luna's involvement is significant because it represents a rare moment when a member of Congress takes a direct interest in astronomical research, especially research that touches on questions about extraterrestrial technology. Her letter acknowledged the importance of the data and called for NASA to prioritize its release, despite the administrative complications caused by the shutdown. It was a shot across the bow, a signal that at least some elected officials recognize the stakes involved. But Luna's efforts also highlight a deeper problem. The fact that it takes congressional intervention to release routine scientific data reveals how fragile our systems are. We like to think of space exploration as above politics, as a pure pursuit of knowledge that transcends partisan squabbles. But the reality is that everything NASA does depends on federal funding, federal employees, and federal bureaucracy. When that system breaks down, even for a few weeks, the consequences ripple through the entire enterprise. The timing of the shutdown could not have been worse. October 1st was not just any date. It was the beginning of the fiscal year, the moment when government funding needs to be renewed or agencies stop operating. Congress had months to pass a budget. They knew the deadline was coming, and yet, as has become depressingly routine in American politics, they failed to reach an agreement in time. The government shut down, and with it, the flow of scientific data ground to a halt. NASA employees who manage the HiRISE camera, who process the raw images, who prepare them for public release, were furloughed. They were told to go home and wait until Congress figured out how to fund the government again. This is standard procedure during shutdowns. Non-essential functions cease. Only mission-critical operations continue. But here's the question that nobody seems able to answer satisfactorily. How is releasing data about an interstellar object not mission-critical? 3I-ATLAS represents a unique scientific opportunity. It is only the third confirmed interstellar visitor we have ever detected. It exhibits multiple anomalies that challenge our understanding of cometary behaviour, and it is here, right now, passing through our solar system at a time when we have spacecraft positioned to observe it. If there was ever a moment to prioritise rapid data release, this is it. Yet the bureaucratic machinery of government operates according to its own logic, indifferent to astronomical urgency. Loeb has been careful not to attribute the delay to malice or conspiracy. He does not think NASA is deliberately withholding the HiRISE images because they show something shocking or inexplicable. His assessment is simpler and in some ways more frustrating. Stupidity, not conspiracy. Bureaucratic inertia, not cover-up. The system is broken, not because people are trying to hide the truth, but because the system itself is poorly designed to handle situations like this. But that distinction, while important, does not make the situation any less infuriating. Whether the delay is due to conspiracy or incompetence, the result is the same. Scientists cannot access the data they need, the public cannot see the images that might resolve ongoing debates. And every day that passes makes future observations more difficult as 3I-ATLAS recedes into the distance. The high-rise image is particularly important because of what it might reveal about the object's structure. With a pixel resolution of 30 kilometers, we could potentially see whether 3I-ATLAS is a single cohesive body or a cluster of smaller fragments held together by weak gravitational forces. We might be able to measure the brightness of individual pixels and thereby constrain the object's surface area and albedo more precisely. We could look for asymmetries in the coma, hints of jetting activity, evidence of rotation or tumbling. All of this information matters. It matters for determining whether 3I-ATLAS is a natural comet, as most scientists assume, or something more unusual. It matters for understanding how interstellar objects form and evolve, and it matters for planning future observations, both of this object and of others that will inevitably follow. The Vera Rubin Observatory in Chile is expected to discover new interstellar visitors every few months once it becomes fully operational. Each one will be a fleeting opportunity. We need to develop better procedures for rapid data sharing, better coordination between agencies, better insulation of time, critical science from political disruption. Loeb's proposed solution is straightforward. Create explicit protocols that designate certain types of astronomical observations as high priority, requiring expedited release regardless of government shutdowns or budget crises. Make it a matter of policy that data about interstellar objects gets shared immediately, within hours or days of acquisition, not weeks or months later after bureaucratic review. Treat these events like what they are, rare and precious opportunities to study visitors from beyond our solar system. Would such a policy solve everything? No. There will always be legitimate reasons for delays. Equipment malfunctions, data corruption, the need for calibration and validation. Science cannot be rushed beyond a certain point without sacrificing quality. But there is a vast difference between careful scientific review and administrative paralysis. Right now we're experiencing the latter, and it is unacceptable. The political dimension of 3I-ATLAS extends beyond just the high-rise situation. There are broader questions about how we handle discoveries that might have implications for extraterrestrial intelligence. If an object were confirmed to be technological, not natural, how would that information be released? Who would make the announcement? What protocols exist, if any, for managing public communication about such a discovery? The answer is unsettling. There are no formal protocols. The SETI community has a set of guidelines, originally drafted in the 1980s and updated periodically, that outline how researchers should handle potential detections of alien signals. But those guidelines are voluntary, not legally binding, and they do not specifically address the scenario of discovering alien technology in our solar system. We are, to put it bluntly, making this up as we go along. This lack of preparedness creates opportunity for confusion, miscommunication, and potentially panic. If NASA or another space agency discovered evidence of extraterrestrial technology, they would face immense pressure to release that information immediately while simultaneously needing to verify their findings before making any public statements. The tension between transparency and accuracy would be enormous, and in today's political climate, where trust in institutions is low and conspiracy theories spread rapidly online, managing such an announcement would be extraordinarily difficult. The 3I-ATLAS case, even without any confirmed evidence of technology, gives us a preview of these challenges. Loeb's public statements about the object's anomalies have generated significant media attention and public interest. Some people are excited by the possibility that we might be observing alien technology. Others are skeptical, viewing Loeb as an attention seeker or sensationalist. The scientific community is divided, with some researchers supporting Loeb's call for thorough investigation and others dismissing his concerns as overblown. Into this complex environment, throw in a government shutdown and delayed data release, and you have a recipe for speculation and distrust. If NASA appears to be withholding information, even for mundane bureaucratic reasons, it feeds narratives about cover-ups and hidden knowledge. The longer the delay continues, the more people will wonder what NASA is hiding. And while the answer is probably nothing, Probably just typical government inefficiency, the appearance of secrecy does real damage to public trust. Luna's intervention helps to some degree. Her willingness to publicly push for data release signals that there is political oversight, that elected officials are paying attention and demanding transparency, but it also reveals how dependent scientific progress has become on individual champions within government. What happens if Luna moves on to other issues? What happens if future interstellar visitors arrive during periods when no member of Congress happens to care about astronomy? Do we just accept that crucial data might go unreleased? The structural problem runs deeper than any single shutdown or any single object. We have built a scientific infrastructure that depends heavily on federal funding and federal institutions, which makes it vulnerable to political disruption. Private companies and international collaborations can help fill some gaps, but they cannot replace the scale and coordination that government agencies provide. SpaceX can launch telescopes, but it cannot compel data sharing across multiple observatories. The European Space Agency can fund missions, but it cannot force NASA to release information faster. So we are left with an uncomfortable truth. The most important astronomical discovery of the decade might be sitting on a hard drive somewhere at the University of Arizona, where the high-rise operations center is located. Inaccessible, because Congress could not pass a budget on time. And even when the shutdown eventually ends, as it inevitably will, there is no guarantee that the lessons will be learned, that future shutdowns will not cause similar disruptions. Loeb argues that this needs to change, that we need systemic reform, not just for 3I-ATLAS but for all future interstellar visitors. That scientific data about objects from beyond our solar system should be treated with special urgency, protected from the usual bureaucratic delays. Is he right? Almost certainly. Will anything actually change? That remains to be seen. The political dimension of 3I-ATLAS is less glamorous than the scientific mysteries. There are no equations to solve, no observations to analyse, just the grinding frustration of dealing with dysfunctional institutions. But it matters just as much, because all the sophisticated telescopes and brilliant scientists in the world mean nothing if the data they generate cannot be shared in a timely manner. And if we cannot get this right for 3I-ATLAS, what hope do we have for handling the next interstellar visitor? Or the one after that? Or the first genuine signal from an alien civilization? These are not hypothetical concerns. Interstellar objects are passing through our solar system regularly. We only started detecting them recently, because our telescopes were not sensitive enough before. But as our observational capabilities improve, we will find more. Many more. The Vera Rubin Observatory alone could discover dozens per year. Each will present a window of opportunity measured in weeks or months. And if our systems cannot adapt, if we remain paralysed by political dysfunction and bureaucratic inertia, we will miss those opportunities. We will watch helplessly as visitors from distant star systems slip past us, unexamined, their secrets preserved only because we were too disorganised to look. The high-rise image will eventually be released. The shutdown will end, funding will resume, and the data will become available. But the delay itself is a failure, a preventable failure that highlights systemic weaknesses we can no longer afford to ignore. 3I-ATLAS is teaching us many lessons. Some are about astrophysics and cometary behaviour, but one of the most important lessons has nothing to do with science at all. It's about politics, bureaucracy, and the fragile infrastructure that enables discovery. And it is a lesson we urgently need to learn. Chapter 9. Juno's Last Chance. There is a spacecraft right now orbiting Jupiter that was never supposed to become part of the 3I-ATLAS story. Juno launched from Cape Canaveral in August 2011 with a specific mission: study Jupiter's composition, map its gravitational and magnetic fields, probe the mysteries of the solar system's largest planet. For over a decade, Juno has been doing exactly that, spinning in its highly elliptical orbit, swooping close to Jupiter's cloud tops before sailing back out to safer distances, collecting data that has revolutionized our understanding of gas giants. Juno was scheduled to end its mission in September 2025. The plan was straightforward. After years of productive science, the spacecraft would be deliberately steered into Jupiter's atmosphere, burning up to avoid any possibility of contaminating Europa or other potentially habitable moons. A noble death for a spacecraft that had served humanity well. But then 3I-ATLAS was discovered, and suddenly Juno found itself presented with an unexpected opportunity. On March 16th, 2026, 3I-ATLAS will pass within 53.6 million kilometres of Jupiter. That is close, astronomically speaking. Close enough that a spacecraft already orbiting Jupiter could potentially be redirected to intercept the interstellar visitor's path. Avi Loeb, working with Adam Hibbard and Adam Crowell, calculated the precise manoeuvres required. The numbers are daunting but not impossible. Juno would need to execute what is called a Jupiter-Oberth manoeuvre. This involves two precisely timed engine burns. The first, on September 9th, 2025, would lower Juno's perigove, the point of closest approach to Jupiter, 8 days before the spacecraft was originally scheduled to plunge to its death. The second burn would occur at that lowered perigove, using Jupiter's intense gravity to slingshot Juno onto an intercept trajectory with 3I-ATLAS. The total delta V, the change in velocity required, is 2.6755 km per second. That is a significant demand on Juno's fuel reserves. The spacecraft has been operating for over 14 years. Its main engine has not been used since 2016, when concerns about the tank pressurization system caused NASA to abort planned maneuvers. Attempting to fire it now carries real risk. The engine might not work, or worse, it might catastrophically fail, ending the mission immediately. But if it works, if the engine fires successfully and Juno can reach 3I-ATLAS, the scientific payoff would be extraordinary. A close flyby, potentially as near as 27 million kilometres, with instruments designed for planetary science, turned toward an interstellar visitor. No telescope on Earth or in Earth orbit will match that proximity. Not even close. What could Juno see? What data could it gather that ground-based observatories cannot? Start with the basics. Juno carries a visible light camera called JunoCam. It was included primarily for public engagement, allowing people to see Jupiter's swirling clouds in stunning detail. But JunoCam could photograph 3I-ATLAS from a distance, measured in tens of millions of kilometres rather than hundreds of millions. That means higher resolution, clearer, detail, the ability to discern structure and features that are invisible from Earth. Then there is Juno's near-infrared spectrometer, GIRAM. This instrument maps temperature and composition by analysing the infrared light emitted or reflected by objects. Applied to 3I-ATLAS, GIRAM could detect heat signatures from the nucleus, map the distribution of volatiles in the coma, identify specific molecules that are difficult or impossible to observe from Earth. If the object is heated by internal processes rather than just solar radiation, GIRAM might be able to detect that anomaly. Juno's magnetometer, designed to study Jupiter's powerful magnetic field, could search for any magnetic signature from 3I-ATLAS. Natural comets do not have their own magnetic fields. They are chunks of ice and rock, magnetically inert. But if 3I-ATLAS was somehow technological, if it contained metallic structures or electrical systems, there might be a detectable magnetic anomaly. It is a long shot, but the magnetometer would be sensitive enough to notice. The microwave radiometer, MWR, probes beneath the surface by measuring thermal emission at multiple wavelengths. For Jupiter, this allows scientists to see through the cloud layers and map temperature at different depths. For 3I-ATLAS, MWR could potentially distinguish between a solid nucleus and a rubble pile, between dense material and loosely bound fragments. It could provide information about internal structure that no optical telescope can access. Juno's gravity science instrument uses precise tracking of the spacecraft's velocity to measure gravitational fields. This was crucial for understanding Jupiter's interior mass distribution. Applied to 3I-ATLAS, even a distant flyby could place constraints on the object's total mass. If the gravity measurement yields a mass inconsistent with the observed size and activity, that would be significant. Very significant. The energetic particle detector and the radio and plasma wave sensor could search for any unusual particle emissions or electromagnetic signals. If 3I-ATLAS is outgassing normally, these instruments would detect the characteristic signature of ionized molecules interacting with the solar wind. But if there were artificial radio transmissions, even weak ones, Juno might pick them up. The probability is low, but the instruments are there, and they would be listening. Finally, Juno's ultraviolet spectrograph could analyse the composition of gases around 3I-ATLAS with far greater precision than is possible from Earth. UV spectroscopy reveals details about molecular structures, abundances, temperatures. It could confirm or refute claims about water content, detect trace elements, provide a complete chemical inventory of the outgassing material. All of this data, gathered from millions of kilometres closer than any Earth-based observatory, would represent the most detailed study of an interstellar object ever conducted. It would not require building a new spacecraft or launching a dedicated mission. It would simply require NASA to approve the manoeuvre, ensure Juno's engine can still fire, and execute the burns with the precision that the agency is famous for. So why has this not happened yet? The obstacles are partly technical and partly political. On the technical side, there is genuine uncertainty about whether Juno's propulsion system is still functional. The main engine was designed for deep space manoeuvres during the cruise phase and for Jupiter orbit insertion. After that, it was supposed to be used periodically to adjust Juno's orbit. But the pressurization issues in 2016 forced mission planners to abandon those adjustments. The spacecraft has been operating in its original science orbit ever since, using its smaller reaction control thrusters for attitude adjustments, but leaving the main engine dormant. Can an engine that has not fired in 9 years still work? Maybe, maybe not. Engineers have examined the telemetry data and believe there is a reasonable chance of success. But reasonable is not certain, and if the engine fails to start, or, worse, suffers a catastrophic malfunction, Juno would be lost. Not at the end of its planned mission, after years of successful science, but in a risky attempt to chase an interstellar comet. That would look bad. It would invite criticism from people who think NASA should stick to its primary objectives rather than pursuing speculative opportunities. On the political side, extending Juno's mission requires funding. The spacecraft was scheduled to terminate in September 2025 because that is when its approved budget ends. Congressional appropriations work on specific timelines. Missions receive funding for defined periods. When those periods expire, the funding stops and the mission ends. Extending Juno to March 2026 and beyond would require additional money, additional oversight, additional justification to Congress. This is where Anna Paulina Luna's letter becomes relevant again. By formally recommending that NASA consider using Juno to observe 3I-ATLAS, Luna provided political cover for mission extension. She gave NASA a reason to request additional funding, a rationale that goes beyond just wanting to keep a successful mission alive. But letters from Congress are not the same as appropriations. They signal support, but they do not automatically translate into budget allocations. There is also the question of mission priority. NASA operates dozens of spacecraft across the solar system and beyond. Every dollar spent extending Juno is a dollar not spent on something else. Other missions, other priorities, other scientists who have their own compelling reasons for needing resources. The agency has to balance competing demands, allocate limited funds, justify every decision to oversight committees. Choosing to redirect Juno toward 3I-ATLAS means choosing not to do other things. That calculation is not simple. Avi Loeb, unsurprisingly, believes the decision is obvious. The scientific value of a Juno flyby far exceeds the risks and costs. Interstellar objects are rare. 3I-ATLAS might be 7 billion years old, a pristine sample from the Milky Way's thick disk, carrying information about galactic evolution that cannot be obtained any other way. Juno is already there, already operational, already paid for. Using it to study 3I-ATLAS is not a new mission. It is an opportunistic extension of an existing one. The delta V required is within the spacecraft's theoretical capabilities. The observation window is well defined. Everything aligns. But Loeb is a scientist, not an administrator. He can advocate for the flyby, write papers calculating the trajectories, communicate with Congress, generate public interest. What he cannot do is make NASA's decisions for them. That authority rests with the agency's leadership, who must weigh scientific potential against operational risk, balance stakeholder interests, navigate bureaucratic and political constraints. As of today, October 31st, 2025, NASA has not officially approved the Juno manoeuvre. The window for the first burn, September 9th, has not yet been decided. Time is running short. Every day that passes without a decision makes the opportunity harder to execute. Spacecraft trajectories are not infinitely flexible. There is an optimal time for each manoeuvre, and if that time is missed, the required delta V increases, the risks multiply, the chances of success diminish. The September 9th date is significant for another reason. It falls only 8 days before Juno's original termination date. If NASA approves the 3I-ATLAS flyby, they are essentially saying that the spacecraft will not be deorbited as planned. They are committing to an extended mission, and if the engine fails to fire or something goes wrong, they will have to explain why they risked Juno on what critics might call a wild goose chase. But here is the counter-argument, the one that Loeb and others keep making. If we do not try, we learn nothing. 3I-ATLAS will pass Jupiter in March 2026, whether Juno observes it or not. It will continue out of the solar system, never to return, taking with it whatever secrets it holds. This is the only opportunity we will ever have to study this object up close with a spacecraft. If we let that opportunity slip away because we were too risk-averse or too bureaucratically constrained, what does that say about our priorities? What does it say about humanity's willingness to pursue knowledge, even when it requires courage and flexibility? The March 16th flyby is not just about 3I-ATLAS. It is about establishing precedents for future encounters. Over the coming decades, we will discover more interstellar visitors. Some will pass closer to Earth, some farther away, some be detected months in advance, giving us time to plan dedicated missions. Others will appear with little warning, offering only brief windows for observation. How we respond to 3I-ATLAS will shape how we respond to those future visitors. If we successfully redirect Juno, if the spacecraft gathers valuable data, if we demonstrate that existing missions can be adapted to study interstellar objects, that sets a powerful precedent. It shows that we are nimble, opportunistic, willing to seize unexpected chances when they arise. But if we fail to act, if bureaucratic caution and risk aversion prevent us from even attempting the observation, that also sets a precedent. It signals that our space program is rigid, unwilling or unable to adapt to new discoveries, more concerned with avoiding failure than pursuing breakthrough science. The Juno decision also matters because of what might happen at perihelion. If 3I-ATLAS does something unexpected when it's hidden behind the Sun, if it maneuvers or releases probes or exhibits behaviour that cannot be explained naturally, the March flyby becomes even more critical. It would be our chance to gather definitive data about an object that has already demonstrated it does not fit our models. But if nothing unusual happens at perihelion, if 3I-ATLAS behaves exactly like a normal comet, the March observation is still valuable for understanding the composition and structure of an ancient interstellar visitor. This is what makes the decision so difficult for NASA. They are being asked to commit resources based on incomplete information. They do not yet know what will happen at perihelion. They do not know how active 3I-ATLAS will be in March, how bright, how easy to observe. They are being asked to take a calculated risk, to gamble on the possibility that this object is worth the effort and expense of redirecting Juno. From a pure scientific standpoint, the gamble is justified. The potential payoff is enormous, and the costs are relatively modest. Juno was going to end anyway. Using it for one more mission, one more observation, one more contribution to human knowledge before its fiery demise in Jupiter's atmosphere seems like an obvious choice. But organizations like NASA do not operate on pure scientific logic alone. They operate within complex political, financial, and institutional constraints that do not always align with what scientists think is the right decision. So we wait. We watch. We hope that the engine will be fired, that Juno will be redirected, that in March 2026 we will get our best and perhaps only close look at 3I-ATLAS. But if that does not happen, if NASA decides the risks outweigh the rewards, or if funding cannot be secured, or if some other obstacle prevents the flyby, then Juno will stick to its original plan. It will make a few more orbits of Jupiter, collecting the last scraps of data from its primary mission, and then on a date in late September it will dive into the planet's atmosphere, burning up like a meteorite, its work complete, and 3I-ATLAS will pass Jupiter in March, 53.6 million kilometers away, unobserved by any spacecraft, its mysteries intact, drifting back into the darkness between stars, leaving behind only the questions we were too cautious to answer. Chapter 10. The Thick Disk Origin. Mystery. Imagine an object older than the Earth, older than the Sun, older than the entire solar system by billions of years, an ancient wanderer that formed when the universe was young, when galaxies were still assembling themselves, when the first generation of heavy elements was just beginning to enrich the interstellar medium. Now imagine that object passing through our solar system right now, close enough to study, carrying within its structure information about conditions that existed long before anything in our local neighbourhood was born. That is 3I-ATLAS, or at least that is what 3I-ATLAS might be. The evidence for its extraordinary age comes from trajectory analysis. When you trace the object's path backward through the galaxy, accounting for the gravitational influence of stars and the overall rotation of the Milky Way's disk, you can estimate where it came from and how long it has been travelling. Matthew Hopkins from the University of Oxford, along with colleagues at the Otatai Oxford team, performed this analysis shortly after 3I-ATLAS was discovered. Their conclusion was startling. 3I-ATLAS likely originated from the Milky Way's thick disk, and if that is true, it is probably between 7 and 11 billion years old, maybe more, older than any comet humanity has ever studied, older than the planetary systems we are familiar with, a genuine relic from the early epochs of galactic history. To understand why this matters, you need to understand what the thick disk is. Our galaxy has structure. It is not just a random collection of stars, but an organised system with distinct populations. The most obvious feature is the thin disk, a relatively flat region about 1,000 light-years thick where most of the galaxy's star formation happens. Young stars, rich in heavy elements, orbiting the galactic centre in roughly circular paths. The Sun lives in the thin disk, so do most of the stars you see when you look up at night, but surrounding and permeating the thin disk is another population, the thick disk. Older stars, metal poor, with orbits that carry them up and down through the galactic plane, thousands of light-years above and below the midline. These stars formed billions of years ago, when the Milky Way was younger, smaller, less chemically enriched. They represent a different era of galactic evolution, a time when conditions were very different from what we observe in the thin disk today. 3I-ATLAS exhibits a vertical velocity component, a motion perpendicular to the galactic plane, that is, consistent with thick disk objects. When you integrate its trajectory backward, it does not stay confined to the thin disk like most interstellar visitors would. Instead, it ventures far above and far below the galactic midplane, oscillating through a much larger volume of space. That vertical excursion is the signature of an old object, one that has been scattered by gravitational interactions over billions of years, gradually accumulating the random velocity kicks that pump objects into thicker, more diffuse orbits. The implications are profound. If 3I-ATLAS is indeed a thick disk object, it formed around a star that no longer exists. Or if that star does exist, it is so far away and so old that it would be unrecognisable compared to the Sun. Thick disk stars are metal poor because they formed before multiple generations of supernovae had enriched the interstellar medium with heavy elements. This means 3I-ATLAS, if it is a comet, would have formed in a very different chemical environment than solar system comets. Solar system comets contain water ice, carbon dioxide, methane, ammonia, and complex organic molecules. They are products of a relatively metal-rich nebula, the cloud of gas and dust that collapsed to form the Sun and planets 4.6 billion years ago. But a comet from the thick disk would have formed in a much more pristine environment. Less carbon, less nitrogen, less of the heavy elements that we take for granted. Mostly hydrogen, helium, and whatever oxygen could combine with hydrogen to make water. This raises a question. If 3I-ATLAS is so old and formed in such a different environment, why does it look like a normal comet? Why does it have a coma and tail, outgas volatiles, behave in ways that are familiar from studying objects in our own solar system? Should not 7 billion years of cosmic ray bombardment and micrometeorite impacts have altered its surface beyond recognition? Should not the harsh environment of interstellar space have stripped away volatiles, leaving behind only refractory material? The answer might be that we are underestimating how well preserved interstellar objects can be. Space is cold. Colder than any freezer on Earth. 3 Kelvin, the temperature of the cosmic microwave background. At that temperature, chemical reactions essentially stop. Volatiles do not sublimate. Ice is as stable as rock. An object drifting through the galaxy, far from any star, would experience almost no heating, no erosion, no degradation. It would simply exist, frozen in time, for eons. Only when 3I-ATLAS entered the inner solar system, approaching the Sun, would it begin to warm up. The surface would heat, volatiles would sublimate, and suddenly, after billions of years of dormancy, it would become active. It would look like a comet because it is a comet, just an absurdly old one that has been in cold storage for most of cosmic history. But there is a complication. Recent analysis by a team led by Xavier Perez-Couto from Universidad da Coruña suggests that 3I-ATLAS might not be from the thick disk after all. They traced its trajectory back through 4 million years of galactic history, examining every star in the solar neighbourhood that might have gravitationally perturbed its path. And they found nothing. None of the nearby stars could explain 3I-ATLAS's current trajectory. None of them scattered it, or deflected it, or ejected it. The object appears to have been travelling on its current path for a very long time, unaffected by local stellar encounters. This led Perez-Couto's team to propose a different origin. Not the thick disk proper, but the transition region between the thin and thick disk. A frontier zone where stellar populations mix, where old stars from the thick disk orbit alongside younger stars from the thin disk. 3I-ATLAS, in this interpretation, is still ancient, potentially 10 billion years old. But it did not come from the deepest regions of the thick disk. It came from the border, from a place where galactic evolution is complex and poorly understood. This might actually be more interesting than a pure thick disk origin. The transition region is where the Milky Way's early history meets its more recent evolution. Objects from that zone carry information about both eras, about the processes that built the thick disk and the processes that formed the thin disk. Studying such an object gives you a glimpse into galactic structure and history that you cannot get from objects born in one population or the other. But it also complicates the age estimate. If 3I-ATLAS is from the transition region, it could be 7 billion years old, 10 billion years old, or anything in between. The uncertainty is large because we do not have precise constraints on the conditions in that region or the timing of star formation there. We are making educated guesses based on galactic models and statistical arguments, not direct measurements. What we really need is a chemical analysis. If we could determine the isotopic ratios of elements in 3I-ATLAS, measure the abundance of different molecules, compare its composition to solar system comets, and to theoretical predictions for primordial material, we could constrain its age and origin much more precisely. That is exactly what the James Webb Space Telescope observations in August and December were supposed to provide. But as with so many aspects of this investigation, the data are still being analysed, the results not yet published, leaving us in a state of educated speculation rather than definitive knowledge. The age question matters for multiple reasons. First, it affects the probability that 3I-ATLAS could be technological rather than natural. If it is 7 billion years old, it would have been created by a civilization that arose billions of years before humans, billions of years before Earth even existed. That is not impossible, but it is statistically less likely than an object from a more recent era. Older means rarer, means fewer opportunities for civilizations to have built it. Second, the age affects our interpretation of the object's trajectory. An ancient object would have experienced billions of years of gravitational perturbations, random encounters with stars and molecular clouds, chaotic orbital evolution. Its current path through the solar system might be essentially random, the product of countless small deflections over cosmic time. But a younger object, say only a few 100 million years old, would have a trajectory more closely tied to its origin star. Its path could be traced back with greater confidence, possibly even identifying the specific system it came from. Third, the age affects what we can learn from 3I-ATLAS about planet formation and galactic evolution. A 7 billion-year-old comet is a direct sample of the material that existed in the Milky Way during what astronomers call cosmic noon, the peak era of star formation when galaxies were most active. That was a very different universe, smaller, denser, more chaotic. Studying material from that epoch gives us ground truth for theoretical models of how galaxies assemble and evolve. A 10 billion-year-old comet is even more extraordinary. 10 billion years ago, the universe was only 3.7 billion years old. Galaxies were still in their infancy. The Milky Way had not yet taken its current shape, and any planetary system that formed back then would have been built from material that was almost pristine, barely enriched by earlier generations of stars. If 3I-ATLAS is that old, it is not just a comet. It is an archaeological artifact from the dawn of galactic complexity. But here is where things get philosophically interesting. If 3I-ATLAS is billions of years old, and if intelligent civilizations can arise around old stars, then it is at least conceivable that this object encountered or was created by intelligences that predate humanity by unimaginable spans of time. Not thousands of years older, not millions, but billions. Civilizations that might have risen, flourished, and either died out or evolved into something unrecognizable long before Earth's sun even ignited. This is the version of the zoo hypothesis that nobody likes to talk about. Not the idea that young civilizations like ours are being observed by contemporaneous aliens, but the idea that we live in a galaxy that has been colonized and recolonized over and over across billions of years, that the Milky Way is ancient, and that intelligence has arisen countless times in its history, each instance leaving traces, artifacts, structures that persist long after the civilizations themselves are gone. If that is true, then 3I-ATLAS being technological does not require it to have been launched yesterday, or even 1,000,000 years ago. It could be a billion-year-old probe, an automated explorer from a dead civilization still carrying out its mission long after its creators turned to dust. Or it could be a 10-billion-year-old remnant of a galactic infrastructure we cannot even imagine, a piece of ancient engineering drifting through space because whatever purpose it once served has been obsolete for eons. This sounds like science fiction. And maybe it is, probably it is, but the age of 3I-ATLAS forces us to confront the reality that our galaxy has existed for a very long time, and that the history of intelligence within it might be vastly longer and more complex than we assume. If we treat every anomalous object as necessarily recent, as necessarily tied to civilizations that still exist, we are imposing human timescales on processes that operate on cosmic timescales, and that might be a profound category error. The thick disk origin mystery, then, is not just about where 3I-ATLAS came from, or how old it is. It is about expanding our conceptual framework to include the possibility that some of what we observe in the galaxy is not contemporary but ancient, that we might be looking at relics rather than active systems, fossils rather than living organisms, and if 3I-ATLAS is such a relic, if it really is 7 or 10 billion years old, then the anomalies we have been discussing take on a different character. They are not necessarily evidence of recent alien activity. They could be evidence of extremely ancient alien activity, of engineering done so long ago that the very concept of who built it and why becomes almost meaningless. Or more likely, they are evidence of natural processes we do not fully understand, of cometary behaviour in extreme environments, of physical phenomena that only occur in objects that have spent billions of years in interstellar space. The universe is strange. It does things that surprise us, and just because something is old does not mean it is artificial. But either way, the age of 3I-ATLAS matters. It changes the context. It forces us to think on longer timescales, to consider possibilities that go beyond our usual assumptions. And that, ultimately, is what makes this object so valuable. Not because it is definitely alien or definitely natural, but because it challenges us to expand how we think about the cosmos and our place within it. 3I-ATLAS is teaching us that the galaxy is older and more complex than our parochial solar system perspective usually acknowledges. That objects can survive for timescales that dwarf human civilization, that the Milky Way has a deep history, and that pieces of that history occasionally pass through our neighbourhood, offering us brief opportunities to study eras that otherwise remain forever out of reach. Whether it is natural or technological, whether it is 7 billion years old or 10, whether it came from the thick disk or the transition region, 3I-ATLAS is a messenger from the deep past. And the message it carries is simply this: the galaxy you live in is ancient. It has seen things you cannot imagine. And sometimes, if you are patient and vigilant and lucky, it sends you a reminder of just how much came before.